Hello everyone. Welcome to Systems at Scale 2023 Winter Event. I'm Biren Damani, Engineering Manager at Meta, and it's a pleasure to welcome you all. As a member of the Core Systems organization, my team and I are dedicated to building Meta's private cloud infrastructure, which serves as a bedrock across Facebook's extensive array of products and services. I am eager to see and connect with all the like-minded systems engineers and industry experts. At this conference, our focus is primarily on focusing on practical aspects of building large-scale distributed systems to solve real-world problems. These systems form the backbone of today's digital landscape across both consumers and businesses. Furthermore, the systems are pivotal in supporting and refining the ever expanding field of AI infrastructure. Ultimately, the systems are the cornerstone of enabling global users to effortlessly access information and technology while guaranteeing the fundamental aspects of performance, scalability, and reliability. Before we introduce our first talk, I want to give everyone a sense of what to expect for the rest of the day that is full of exciting speakers from Google, Microsoft, Uber, Figma, and Meta. The agenda is organized into three distinct sessions. The first session will be focused on scaling AI platform, followed by a session that deep dives in some of the large-scale infrastructure systems built to solve real-world problems. And finally, we wrap up with a deep dive in the world of performance, reliability, and efficiency at scale. At the end of each session, we'll have a Q&A moderated by Shilpa Lavande, who is an engineering director at Meta. So without further ado, let's discuss and dive into the heart of one of the most intriguing topic in our industry, AI. As the influence of artificial intelligence continues to permeate every facet of our daily lives, it is imperative to scale infrastructure to support the ever-growing complex and diverse AI workloads. Please join me in welcoming Meta engineers Bikash Sharma, Leon Yan, and Hafan, who will be sharing insights and importance for investing in multi-tenancy for AI inference at meta scale. They will guide us through various optimization strategies that enable significant infrastructure cost savings while serving diverse AI workloads. Take it away.
Hello, my name is Bikash Sharma. I'm a software performance engineer at Meta working on ads, AI, inference efficiency with emphasis on infrastructure optimizations. Together with my colleagues Leon, Ha, and Zen, we will share our efforts, progress, and learnings from 0 to 1 bootstrapping of AI inference multi-tenancy at meta scale. This will be the agenda of the talk. I'll start with a brief introduction covering related background, motivations, and talk sub-themes. I will then hand it over to my colleague Leon, who will go over the AI multi-tenancy infrastructure at Meta. Ha will then summarize onboarding ads inference, which is a very important class of AI inference workloads at Meta, to multi-tenancy and share a few interesting aspects of this productionization journey. I will then conclude the talk with key learnings, takeaway, and call to action to further this domain of work. This talk overview teaser slide is simply a mind map, eye chart capturing the various sub-themes of this presentation. As you can see, each color-coded collection of rectangles here represents one such logical flow of the talk, with multi-tenancy for AI inference being the central piece. So let's begin with understanding what is AI inference. As we know, training and inference are two important stages in building ML models. Training is the process of teaching an ML model how to make predictions, while inference is the process of using such trained ML models to make predictions. This pipeline harnesses representative class of ML models, including the popular deep learning recommendation models, as well as the recent large language models like GPT. Inference systems are complex, real-time, built with strict performance requirements like low latency and high throughput. And unlike training, inference costs scale with usage of infra resources and with relatively linear infra requirements. Just for fun, let's look at what a AI inference engine itself has to say when asked about what is AI inference. Next, let's look at the hyperscale growth of AI inference workloads at Meta. There are thousands of models with a large spectrum of model complexity, both in terms of compute flops as well as embedding sizes. Some of the large complex models are in the order of hundreds of gigabyte embedding and gigaflop compute complexity. The chart on the right shows the AI model trends over next few years, and as you can see, models are getting more complex in computation as well as size. These models run on tens of thousands of machines, consuming multi-megawatt of data center AI capacity, which in itself is on a non-linear growth trajectory as shown in this chart. The AI inference models are used across a suite of different product offerings at Meta, including ads, feed, IG, as well as Rails. Now, let's take a look at the AI inference hardware landscape at Meta. Meta has traditionally relied on CPU-based servers for running AI inference workloads, but the superlinear growth in the compute and memory requirement of these models have pushed the hardware landscape towards using specialized hardware solutions such as GPUs and custom accelerators like MTIA. AI inference fleet is multidimensional in terms of the diverse infra resource requirements like memory bandwidth, network latency, as well as the hosted workloads, aka ML models. Here I want to highlight the observation that each of the AI inference hardware like CPU, GPU, MTIA has a particular sweet spot in this multidimensional space in terms of their value proposition. Now, let's take a look at the different factors that have influenced the adoption of accelerators to drive AI workloads. First, as AI models increase in size and complexity, as we covered in a few slides earlier, the underlying hardware systems need to provide exponentially more memory and compute while remaining efficient. Accelerators definitely fit the bill here. Second, inference accelerators are designed to be more flexible and adaptable, allowing them to support a broad range of AI workloads. They offer enhanced scalability and efficiency. Third, AI accelerators supplements the processing power of CPU-based servers in our data centers. Fourth, it extends upon the growing industry trend for AI hardware. And fifth, it offers better perf per watt ROI, which is a key component of data center TCO or total cost of ownership. Now let's take a look at what multi-tenancy in the era of AI means. Multi-tenancy refers to the ability to share AI infra resources across a suite of concurrently running models in an efficient and reliable manner. It serves as a key infra lever to capitalize on AI platform offerings. Multi-tenancy offers several advantages, including improved scalability, boost in inference fleet utilization, as well as lower infrastructure cost. Now, let's look at some of the prominent factors that have recently fueled multi-tenancy for AI inference workloads at Meta. AI inference workloads are characterized by being real-time latency sensitive and serving unsteady traffic, and this complements the very concept of multi-tenancy. These AI inference models are unfortunately not able to fully utilize accelerator resources because of the diversity in model characteristics representing different resource bottlenecks as well as performance sensitivity. Therefore, one size fits all constitutes a suboptimal strategy leading to inefficient resource utilization. Multi-tenancy acts as a glue to tightly couple the AI hardware capabilities with emerging workloads requirement towards efficient utilization of underlying infra. Multi-tenancy holds promises as a potential harbinger of infrastructure efficiency and capacity savings. Amongst the various factors favoring multi-tenancy for AI inference that we just discussed in the previous slide, I want to emphasize that diversity of resource characteristics of inference models coupled with a long tail of low complexity, low traffic, and low throughput is a key advocating factor for multi-tenancy. Multi-tenancy for AI inference offers high ROI or return on investment in terms of opportunity sizing. Multi-tenancy can offer up to 30% inference capacity saving. It helps boost inference application performance, example P99 latency, through effective resource isolation and fungible resource allocation. Thank you. This concludes the introduction. I will next hand it over to my colleague Leon, who will cover the multi-tenancy infrastructure at Meta.
Thank you, Bikash, for laying out the landscape of GPU multi-tenancy. My name is Leon Yang. I'm a software engineer from Meta's containers team. In the following section, I will share with you our experience to bootstrap Meta's GPU multi-tenancy infrastructure. If you're interested in exploring improvements to AI efficiency, please follow along. When Bikash first approached my team for supporting GPU multi-tenancy infrastructure, we knew very little bit about this technology. To the best of our knowledge, there are three common types of GPU multi-tenancy solutions: time slicing, software-based multi-tenancy, and hardware-based multi-tenancy, which includes NVIDIA's multi-instant GPU technology. Time slicing simply runs processes in turns. It does not improve GPU efficiency, and therefore it was not in our consideration. In contrast, SMT and HMT support simultaneous multi-tenancy to keep the GPU utilization high. SMT runs a single process that acts on behalf of its managed processes by merging their GPU contexts. HMT instead partitions the GPU in hardware level. Each resulting slice has similar functionalities as the whole GPU. Both solutions are promising in delivering great capacity saving, although it's challenging to choose the right one. Here, I will share with you how we compare the two and why we choose HMT as our infrastructure. When evaluating multi-tenancy approaches, we focus on four main factors: performance, engineering efforts, isolation, and flexibility. Performance is the most obvious factor. In the end, we would like to improve efficiency. If a multi-tenancy solution performs significantly worse comparing to a whole GPU when handling production workload, it wouldn't be viable. Therefore, the first thing we do is to measure peak traffic serving a typical inference model. For both SMT and HMT, we share the same GPU with two processes and ensure that GPU is the bottleneck resource. Then we ramp up the inference request with a P99 target latency. Both solutions measure similar performance comparing to a whole GPU. SMT even outperforms HMT by 7%. However, performance is not the single deciding factor. During our performance experiment, we realized that high engineering efforts could be a barrier to adopting GPU multi-tenancy solutions. Although both SMT and HMT require zero code change thanks to vendor library abstractions, fitting them to existing infrastructure may not be an easy task. The one that better aligns with the infrastructure could be supported with less friction. That leads to our next topic: isolation. Isolation is a key attribute to Meta's server management infrastructure. In previous System at Scale, we talked about how we manage region-wide data centers with RAS, where we use reservation to represent a set of servers. One ongoing work of RAS is to support stacking reservation for server multi-tenancy. For example, a host may have 3 stacking reservations, each runs a different workload from different product. Each stacking reservation has a t-shirt site annotated by its primary resource, GPU in this case. Other resources are allocated proportionally. A major promise of stacking reservation is strict container boundaries, which could not be achieved without comprehensive isolation. Coming back to GPU multi-tenancy, the biggest issue with SMT is its lack of error handling isolation. For example, process A may trigger a hardware exception, and then both process B and C will fail because they run as the single process under the hood. In contrast, if HMT is in use, errors from process A never propagates to its neighbors, making HMT the ideal solutions for a stacking environment. Although HMT is not perfect. As Bikash mentioned earlier, AI inference models has a wide spectrum of diversity. We would like to have a GPU multi-instance infrastructure that quickly adapts to requirements of different models. That's what flexibility measures. The great isolation of HMT actually comes at the cost of flexibility. Because HMT statically partitions GPU resources, it has limited number of partition options. A side effect is that it is possible when some partitions are overloaded while others are partially idle. HMT also has more constraint than SMT regarding repartitioning, making the process significantly slower. It was hard to compromise with HMT's inflexibility, but it turns out to be not as bad as we first thought. There are a few reasons. First, the benefits of having more granular multi-tenancy has diminishing return. HMT seems to be sufficient even for our most lightweight models. Second, non-work conserving seems to be a desirable attribute for stacking environment, as it provides predictable performance. Lastly, we found that we can actually hide the weight reconfiguration cost by doing that in advance on buffer capacities. With all the considerations, we finally incorporate HMT into our infrastructure. This sounds like a win of isolation over flexibility, but that may not be true for all the companies. A key insight is that any existing infrastructure may pivot how we apply GPU multi-tenancy. In order to fully harness its potential, we should treat it as a first-class concept when developing applications, infrastructure, future hardware, and drivers. And that's where we're heading towards. At the time of writing, inference is the largest user at Meta for GPU multi-tenancy. Many products are actively onboarding as well, including generic inference, continuous integration, and developer environment. It is truly an exciting moment with many opportunities and challenges to evolve GPU multi-tenancy technologies. With this, I will hand it over to Ha, who will cover our productionization journey.
Thank you, Leon. I will continue our presentation with how we onboarded multi-tenancy with As Inference Service. So As Inference Service is one of the largest AI inference workloads at Meta that serves hundreds of inference models running on thousands of accelerators and consuming multi-megawatt capacity of data center. In this production journey section, I will talk about 4 topics: how we match a model to multi-tenancy containers. I will also briefly introduce our As Inference Service control plans that empowered autoscaling, our observation during productionization, and future of multi-tenancy. So as mentioned before, Meta's As Inference Service serves hundreds of AI inference models, and these models represent a wide range of model characteristics in terms of their complexities, resource footprints. Hence, diverse container sets are necessary to boost the serving efficiency of As models. This is an eye chart showing the distribution of device compute and memory utilization of inference models running on GPUs, which reflects the resource diversity of different models. Note that we normalize the X and Y axis for anonymity. So now, provided with many container sets and models with different characteristics, we need a good method to map a model to its befitting container set. For this, we do per model offline performance benchmarking under load tests to determine the max throughput a model can attain under some performance constraints like memory, CPU utilization, PCIe bandwidth. Since As Inference serves real-time traffic, we also look at the model traffic pattern. As you can see in this chart, there is a great traffic imbalance across different models at Meta. In fact, some models only serve about 0.05 or 0.1% total traffic, while others may serve 5% traffic. We often use smaller container size like HMT for the models with lower traffic. Next, I would like to talk a little bit about how multi-tenancy interfaces with service control plans at Meta As Inference. Our team uses inference platforms like IPNet or SAP to manage the life cycle of models like load balancing, traffic routing, auto-scaling, and transaction season. It also interfaces closely with the underlying heterogeneous multi-tenant infrastructure. I want to highlight the importance of SAT caller and autoscaling. SAT caller helps us to achieve autoscaling, and the motive of autoscaling is to help us serve real-time traffic efficiently. Looking at this chart, you can see that thanks to autoscaling, we can scale up and down our fleet according to the amount of real-time traffic, and unable to do this will lead to a significant waste in capacity. We observe many benefits from HMT during our productionization process. Firstly, HMT containers has better P99 latency. Secondly, HMT container has better resource distribution compared to the non-HMT containers. And lastly, we also see up to 30% capacity saving depends on the model type from using HMT containers, and that unblocks us many more opportunities for experiments. I will go into more detail. Looking at this chart, you can see that the P95 and P99 latency of HMT containers are less than the P99 and P95 latency of other containers. You may wonder why I mentioned that HMT container has better resource distribution compared to the non-HMT containers. It's because the smaller containers like HMT are easier to be moved around and have more deployment flexibility than the bigger containers. We can see that for the same amount of resource, there are more ways to use HMT resource than other containers. Next, I will talk about our fourth point, which is the future of multi-tenancy. So new service control plans, hardware generation, and better utilization can bring more potential for customizable containers like HMT. I will give you some examples. First, a cooperative multi-tenant aware control plan could facilitate using SMT or a more dynamic HMT in stacking first environments. Second, future generation of accelerator hardware types will be more performant in compute and diverse in resource distributions. Multi-tenancy will empower us to utilize the new hardware types with more flexibility. Third, currently many of our models cannot be onboarded to HMT containers due to the memory utilization bound. So we are exploring offloading models from device memory to host memory, and this will make multi-tenancy achieve a better service efficiency when memory size on device is no longer a constraint for a model. Now I will hand it back to Vikas to talk about our takeaways.
Thank you, Ha. Before closing our talk, we would like to showcase the state of art of multi-tenancy in industry as it exists today to the best of our knowledge. Multiple forms of hardware and software level multi-tenancy solution exist and are being used across private and public clouds to suit their AI workload characteristics. Some of these specific techniques and use cases are shown or summarized in this table. Next, we are going to summarize the key takeaways and lessons for the future. First, the next generation of AI workloads and the AI hardware needs to come closely together to attain the true potentials of multi-tenancy. Second, there is a need for a standardized set of multi-tenant solutions generic across AI hardware and vendors. This will certainly help achieve a streamlined and a high-impact development ecosystem. Finally, AI software framework needs to be aware of the underlying AI hardware multi-tenancy to make a strong use case. This concludes our talk. Happy to take any questions now.
Thank you, Bikash, Leon, and Ha for sharing your insightful perspectives. Building upon the theme of AI workload efficiency at scale, our next speaker is Shazan from Google. He'll be discussing the innovative strategies devised and implemented at Google to enhance sharing and utilization of GPU clusters across diverse AI workloads. Shazan, take it away.
Hello, everyone. My name is Xiao Zhang. I'm a member of the Borg team at Google. Borg is a software component that is responsible for managing all hardware resources at the cluster level. In the first half of my career at Google, I mostly worked on CPU memory resource management. With the advancement of machine learning, I transitioned my interest to more machine learning related hardware resource management. Today, I'm going to present automated GPU sharing at scale. This is a joint work with my colleague Jiafan Zhu at Google. Now, first motivations why we choose to do this project. As we all know, GPUs are very expensive hardware. One single unit of NVIDIA GPU can easily cost tens of thousands of dollars on the market. With the recent advancement of machine learning, such as ChatGPT or BART, the severe competition in this space further fuels the demand of GPU. Here is a third-party research about the graphic unit market size from 2022 to 2032. Today, we're at a market size about 50 billion US dollars. As in the next 7 to 8 years, this market is going to more than $500 billion. With this rapid growth and the market size, even a small percentage of efficiency improvement can translate to millions of dollars saving. And we believe GPU sharing is one of many potential solutions to improve the efficiency. With that, here is the agenda of my talk. First, I will introduce some basics about the GPU hardware. Then I will talk about how we automate the GPU sharing at Google. I will share some deployment experience and the evaluation result. Lastly, I will conclude with some key takeaways. Okay, first, let's talk about the basics of the GPU hardware. There are two major hardware components on a GPU. The first one is compute units. It provides massive parallelism for matrix operations. It's equivalent to the CPU cores on a traditional server. The other component is on-chip memory. It is also known as high bandwidth memory. I will refer to it as HBM in the rest of this talk. This is equivalent to the DRAM on a traditional server platform. For GPU sharing, the limited HBM capacity is a bottleneck resource, as it has limited capacity but needs to be shared by co-running GPU tasks. On the older GPU like a V100 and P100, the HBM is only 16 gigabytes. On a newer platform like A100 or H100, you might have 80 gigabytes of memory or even bigger. When the HBM capacity is exhausted, it will trigger an out-of-memory error. And when that error is triggered, it's fatal. Most likely, the task will fail and crash. Luckily, there's a solution to that. This is called unified memory. Essentially, it creates a virtual memory space that maps both the HBM and the host DRAM. So when the HBM is exhausted, there's no more room, but the page will be swapped from HBM to host DRAM. Because usually the host DRAM is 10x or even more bigger than the HBM. So virtually you will not see the OM anymore, but you have to pay the overhead of slowdown because memory paging, memory swapping between the two takes time. And for GPU sharing, it does not work for all workloads, but luckily we have 13 of workloads that can benefit from it. The targeted workloads for GPU sharing is a single GPU workloads. It could be some researchers trying some research ideas just to validate the model's convergency without a full scale of experiments. And it also could be some production prototype with small data sets and to validate all the configurations without a full-blown flash. Typically for the single GPU workloads, it's less sensitive for sharing and also has a very lightweight touch on the usage, occasionally with some spikes. Here is a table to show the compute usage and HBM usage for single GPU workloads that was running our fleet. On the mean, it has 23% of compute usage and 34% of HBM capacity usage. As you can see, this provides an upside for sharing opportunities. On the 90th percentile, the compute usage is about 68%, and the HBM usage is about 86%. Again, this sort of confirms that the HBM usage is the first bottleneck in terms of resource sharing. We also tried multi-GPU workloads, but found out that it's very sensitive for noisy neighbor. And if you have one replica in the multi-GPU workloads that suffers from GPU sharing, this quickly becomes a straggler in the overall workload and might have a cascading side effect. Because as we all know, the machine learning training, especially training, is mostly running in synchronized fashion, and one straggler can slow down the whole pipeline. As for hardware mechanism, there are two basic ways for sharing. The first one we refer as the static resource partitioning. So in this case, both the compute units and the HBM are statically partitioned among co-running tasks. An example of this mechanism is called NVIDIA's multi-instance GPU, MIG. This type of mechanism provides best resource isolation because everything is physically partitioned, but somehow it limits the sharing outsides. Take the MIG for example. If you have a two-task sharing, MIG can always equally partition the HM space among the two tasks, regardless of their individual resource consumption requirement. Even you have a dynamic partition mechanism available, you still need a prior knowledge to know the individual task resource consumption, then find out the optimal partition point. The second hardware mechanism for sharing we refer as a dynamic resource sharing. So in this case, the computer units are 10 multiplexed in round-robin fashion. This is very similar to the context switch that happens in the Linux kernel. As for the HM capacity, this will be shared dynamically among tasks. So we found out that this will give us better overall performance because all the resources, especially the HBM, can benefit from the resource pooling effect. And this can be, I can give example on both spatial and temporal perspective. By spatial, imagine you have one small task that co-run with a bigger task. So now both of them can maximize the HBM capacity utilization without performance penalty. That's what I refer as a spatial benefit. By temporal benefit, now imagine you have two tasks, both has a very high peak usage, but as long as they did not simultaneously peak, there's still opportunity for them to co-run together and share the device in a harmony fashion without adverse performance penalty. So that is what I refer as a temporal benefits. Of course, dynamic resource sharing will give us our best overall performance, but it also has less guarantee on performance isolation, which we'll address in a software way later. Next, I'm going to talk about how we automate GPU sharing in our fleet. The prerequisite for GPU sharing is that we enable unified memory for tasks that participate in GPU sharing, such that the wound will never happen to them. The automation process has 4 major components, and I will describe them one by one in great details. The first step is extensive real-time telemetry collection. We collect application-level metrics such as steps per second. This is a typical throughput metric for machine learning training workloads. We also collect hardware counters, for example, computer utilization, memory bandwidth utilization, HBM occupancy, etc. We export those telemetries continuously via real-time signals, so there's a feedback loop-driven optimization, as well as long-term database, which is used for post-analysis. The second component is to infer the baseline performance. We explore the natural idle periods during task setup, teardown, or waiting for updates. During those idle periods, we can infer the baseline performance of the other co-running tasks that's sharing GPU with the idling tasks. By doing so, it eliminates the need of profiling or trial runs to get a baseline performance of tasks that participate in the sharing. The third component is the runtime detection of performance anomalies. As we continuously monitor the runtime performance, we can raise a flag if the monitor performance drops to some certain threshold. And in our experience, small percentage of sharing cases are indeed categorized as performance anomalies and suffer performance loss. The last component of this automation process is called cry for help. This is a process introduced to mitigate the performance anomalies. It will reschedule tasks that shows performance anomaly behavior. During this rescheduling, tasks with antagonism behavior will be opted out from feature sharing. We employ a hardware heuristic to identify antagonist tasks. The tasks with the most heavy usage profile will be deemed as antagonist, and therefore we think it's not friendly to share with other tasks in the future. Cry for help greatly reduce the anomaly cases, as we're going to show in the later slides. GPU sharing was deployed into Google's internal GPU cluster in 2020. Immediately after this deployment, we observed significant utilization improvement of GPU devices. In addition to that, we also saw host DRAM and CPU utilization improvement. And this is the first time that we can overcommit GPU capacity at the cluster level. Remember, all this was done during COVID. Despite all the engineers work from home, the demand for GPU never faded away. And with the GPU sharing, this greatly improved their productivity during the industry level supply chain shortage. Here, I want to talk a little bit more about the cluster level utilization improvement. Before I jump into the details of the graph, I want to define some terminology used here. On the y-axis, we show the normalized number of GPUs. Here, the normalized number of GPUs is defined as the total number of GPUs requested by all the jobs, then normalized to the physical capacity of GPU in that particular cluster. So if you see the yellow line point at 1.0, that means 100% of the physical GPUs are occupied. Prior to the GPU sharing, which is indicated by the dashed red line, we have a normalized GPU around 90 to 92%. And there is a few percentage deducted from the 100% due to the holdbacks for things like repairs, updates, maintenance, stuff like that. After we deploy the GPU sharing, which is indicated by the solid blue line, the normalized GPUs is always above 1.0, which means we effectively overcommit GPU capacity. We schedule jobs more than physical capacity can hold, thanks to GPU sharing. And you can see compared to before and after, there's a 20% of delta. This means that we can schedule 20% more jobs at the cluster level. This is a great efficiency boost to our cluster utilization. I also want to talk about a little bit about the cry for help mitigation. Cry for help was introduced as a mechanism to mitigate performance anomalies. In our sharing setup, we allow up to 2 tasks share one physical chip, and we use 50% normalized performance as the threshold to define anomaly. Why 50% normalized performance? If you have 2 tasks sharing, each of them get 50% of normalized performance, then that's the 2 sum up to be 100%, which is the break-even point for sharing. Here, the normalized performance is defined as when the task is sharing, normalized to that performance when the task is not sharing with anyone else. Before the cry for help was introduced, we saw 14% of individual tasks that participated in the sharing drops to under the 50% normalized performance. Once we have the cry for help deployed, and the reschedule can automatically kick in and correct the anomaly behavior, the cases for the performance anomaly dropped from 40% to 5%. I also like to take this opportunity to share some lessons we learned through this large-scale deployment. The first is two-way sharing is more practical. What I mean by two-way sharing, we only allow up to 2 tasks share one GPU device, mostly for 2 reasons. We find out that by putting more tasks on a machine, it naturally increases the CPU and the DRAM demand. And we find out DRAM capacity quickly become a limiting factor on how many GPU tasks you can share on a single host. Another factor for this decision is that the sharing benefit will quickly diminish as the number of corollary tasks increase. Remember, in the early slides, I showed the mean usage for both the HBM capacity and also the compute units. The more tasks you put on the device, the more demanding those tasks will become in a total. The second takeaway lesson is that multi-GPU workloads are very sensitive to noisy neighbor. With the increasing demand for large language model like LLM, the single job may consist thousands of chips, even tens of thousands of chips, and they're super sensitive to the straggler, which will have a cascading effect in this synchronized training fashion. We found out they are less suitable for GPU sharing, at least with the current hardware limitation. When I talk about hardware limitation, we wish there are more hardware enhancements down the road. Most specifically, we'd like to see the dynamic resource partitioning instead of static resource partitioning, and we also want to see the per-process hardware profiling. Some of the hardware counters today is profiled at the device level and cannot be easily broken down by process. Lastly but not leastly, sharing is a choice. It's not a tax imposed on the end user. Here I want to share a story that we had when we first tried to deploy the GPU sharing. We put it as a mandate and opening all the users to the sharing. And some performance benchmark team, they cannot tolerate the noise neighbor issue, and they have to opt out. So by working with the customers, we've led them to choose by themselves and provide incentives for them to adopt. For example, by adopting to this GPU sharing, you may virtually double your quota and you can submit more jobs. So that naturally provide incentives for users that can adopt them and can tolerate the performance. We find that working with users rather than force them will give us a win-win situation. All right, I would like to conclude my talk with some key takeaways. First, GPU sharing is practical and beneficial to certain class of workloads. Of course, it does not work for all workloads, but it does for certain type of workloads that can tolerate the performance penalty, and it will achieve great efficiency at a large scale. The HBM is the key resource in terms of GPU sharing, and you need to find a good way to maximize the utilization on HBM to achieve the maximum performance. Resource pooling has better overall performance than static partitioning, and the benefits comes from both spatial and the temporal fashion. Lastly, we introduce a reactive cry for help to mitigate performance anomalies. It reduced the performance anomalies from 40% to 5% in our case. With that, I'd like to conclude my talk, and thank you for your time.
A big thank you to Shazan for that fascinating exploration of GPU sharing at Google. Now let's switch gears a bit and talk about real-life example of using AI. As we recognize, maintaining and running reliable systems at scale is the foundation of any cloud system. Nitin Gupta and Madhura Parekh, both from Meta, are presenting Beyond the Bus Evolution of AI Ops to improve reliability at scale. This talk promises to walk us through a multi-year journey of embracing AI ops at Meta and share a blueprint for leveraging them to enhance the reliability of large-scale systems. Take it away.
AI ops is the latest buzz in the observability industry. Many companies are leveraging AI to simplify debugging and accelerate investigations for critical incidents. And generative AI is taking the excitement even further. However, when we started, existing systems and workflows at Meta posed several challenges to bringing in AI ops as we knew it in the industry. And we had to evolve it together with many other teams at Meta. Today, we'll talk about the evolution of AI ops at Meta and our multi-year journey to drive down mean time to recovery for incidents. Hi everyone, I'm Nitin. I'm a software engineering manager at Meta. And with me is Madhura, who is a software engineer at Meta. Our talk is broken into 4 parts. We're going to start with examples that motivated us to get onto this journey and the challenges that we saw at Meta to solving those problems. Then Madhura is going to do a deep dive into the technical systems that we built and how we integrated it into the products and workflows at Meta and the impact that it had on the mean time to recovery for incidents and the on-call experience. And we are going to end with key takeaways from our journey along the way. But before we talk about what we built, let's go back in time to 2021. Ads Manager is one of the business critical team at Meta. Advertisers around the world use Ads Manager to create ads and reach millions of users worldwide. This team was seeing close to 100 incidents every 6 months. And if you think about it, that's one incident for every business day. And every time Ads Manager is down, that's a lost opportunity for our advertisers. That's a lost opportunity for the company. And that's a lost opportunity for our users. Nobody wants to see irrelevant ads. And this wasn't unique to just Ads Manager. We were seeing similar trends for many other teams at Meta. Web Foundation, which is a critical team to keeping our site up and running 24/7, was seeing an overwhelming number of incidents. Or Instagram Reels, which was just starting to grow at the time and was seeing close to 4 to 5 days of time to resolve issues. And as we look towards AI ops as a potential solution, we saw several gaps in our monitoring systems. At Meta, we have some of the most scalable infrastructure for observability in the industry. And we have talked about it in the past at Skill Talks. We have a system to store metrics, we have a system to store logs, and we have a system to store traces. But they've grown organically over the years, and they don't talk to each other. So if I'm in the middle of an issue and I'm looking for all my data for a service, there isn't an easy way to find it. I'm stuck finding a needle in the haystack. Actually, multiple haystacks. This leads to knowledge being limited to a few people. People with a very particular set of skills they have acquired over a very long career to hunt down the right data. And there is no way for them to share it with the team quickly. They can write wikis, but at the pace Meta moves, those wikis are outdated very quickly. And with so many issues, so much disconnected data, and only a few people to look at it, it's hard to look at everything. And we had a diverse set of workflows to deal with the situation across the company. All of these challenges meant that we had to fundamentally think about how to solve these problems together with these experts that worked for the disconnected data that we had at Meta. And now Madhura is going to talk about the systems that we built to solve these problems together with some of these people.
Thank you so much, Nitin, for providing that context. Okay, so how can we systematically tackle all of the key challenges that Nitin highlighted? In this portion of the talk, I will do a deep dive into the 3 foundational systems that we evolved across multiple halves to address this. And one thing I really want to call out is that foundations were the key for us. We really had to meet our users in their existing workflows instead of building something from scratch. We worked iteratively with a lot of the on-call teams that Nitin touched upon, but our overall goal was to build a generalized solution that could apply across multiple on-calls and problem domains at Meta. So with that context, let's dive right into the technical details. Our first building block is fully programmable on-call runbooks. So let's double-click into what I mean by that. These are powerful, executable runbooks. They support Python-based authoring, so users have the full power and goodness of Python to codify their manual investigations. We also have decorative SDKs for quickly authoring telemetry queries across all of the underlying data sources at Meta and ML algorithms to further analyze this data. Now, the other side of this is the user experience. And for that, we provide standardized out-of-the-box decorative APIs to produce output UI widgets with intuitive charts and visualizations. So even a noob user with little to no UI expertise can come in and quickly author powerful automated investigation workflows. So this is great. Users are now codifying their previously manual investigations, but it's not that useful without a platform that integrates with users' existing workflows. So for this, we built a fully managed platform that is responsible for orchestrating and deploying these runbooks and providing a host of other convenient features. Our platform integrates with Meta's detection systems to automatically trigger these runbooks whenever an alert fires. And in addition, we also have an interactive UI for users to trigger this runbook on demand. So going back to the Ads Manager case that Nitin touched upon, today Ads Manager is a heavy user of our automated runbook solution. In fact, their analyzers called Detective have been able to codify almost 50% of their manual investigations. So with this, we've managed to tackle a lot of the on-call toil and manual investigation pain points we touched upon earlier. But if we look back to the challenges that Nitin highlighted, a big one that still stands out is that there's tons of observability data at Meta. How do we allow our users to quickly author automated workflows to analyze this data and get meaningful insights? For this, enter our second foundation, analysis algorithms as a service. We've implemented a few fundamental ML algorithms that were scalable at meta scale. And to give you a sense of the scale, we generate billions of data points per day. And our algorithms need to operate at this scale and generate real-time insights in under seconds. Our algorithms library includes algorithms such as fast dimensional analysis, various time series analysis algorithms such as time series correlation, anomaly detection, and others. How we implemented these algorithms to be performant at meta scale is beyond the scope of this talk, but if you're interested, I highly encourage you to check out our blog, which links to a paper we published on this very topic. Now, on top of our algorithms library, we also built a service to actually execute these algorithms and produce insights. So users that are authoring the automated runbooks I covered earlier can just call into our service as they are building their workflows. But that's not all. We also integrated this service with our most visited dashboards and UIs to run these analyses in place in the UI and meet the users where they are coming to investigate issues. So as an example, this is a snippet of one of our top visited dashboards by the Web Foundation team. As you recall, this is one of the most critical teams at Meta, and it's responsible for keeping our website up and running. For this specific situation, there was a spike in web fatals, and our analysis service has already run dimensional analysis on the dashboard and isolated the issue to a specific class of enforcement exceptions. And this is clearly highlighted and available to the on-call when they came in to investigate. So this is awesome. With these two foundations, we have actually addressed most of the pain points that we had highlighted earlier. But now, we wanted to look back and see how can we make investigations at Meta even faster. In 2022, the reliability engineering team at Meta did a breakdown of the worst critical incidents that the company had seen that year. Now at this scale, critical incidents can have a variety of root causes, but pictured here are the top root causes. And the one thing that immediately jumps out is that code and config changes being deployed at the company were accounting for more than 50% of our most critical incidents. So this pointed us to the third foundation I'll cover today, event isolation. Event isolation is our system for ranking thousands of change events happening at the company and isolating them down to the root causing event. For ranking, we've built event ranking ML models that leverage a variety of signals, such as text matching, anomaly detection, context of the owning on-call, and others. On an average, we found that when we deployed our event ranking models to production, they were able to filter out more than 80% of the uninteresting events during an investigation. Today, we focus heavily on config-based event isolation, but we also have work in progress towards supporting code-based event isolation as well. So let me quickly walk you through an example of event isolation in action during a critical alert. For the given spike in the time series, we can see that our event ranking models have already ranked the top 4 most suspicious events. They've also added confidence around this ranking, high or medium confidence, and in addition, we've also added annotations that explain the reasoning for this ranking. I really wanted to call this out. We found that adding these annotations were really key in getting our engineers to trust these insights, and they were less likely to trust them if it was more of a black box. So going back to Ads Manager, if you recall, Nitin mentioned that downtime sieves are the worst critical incidents for this team, and they cause a significant revenue loss for the company as well. So today, Ads Manager actually leverages event isolation heavily to guard against this class of sieves. In fact, just recently, they had an issue where Ads Manager was failing to publish for 10% of its users. And by leveraging event isolation, they were able to quickly root cause and mitigate this in under an hour and prevent a much wider outage. So with these three foundations under our belt, I'll hand it back to Nitin to walk us through the impact and the use cases that are being built on top of these foundations.
Thanks, Madhura, for talking about these foundations. Now that we had this foundation, let's talk about how we used it across multiple use cases at Meta. We will talk about 3 of them here today, but there are many more that we talk about in our blog online. First, we integrated it with Slick. Slick is a system that people use at Meta to store SLOs and track violations against their SLOs so that they can get a monthly report to how they're doing against their SLOs. By integrating with these foundations, people are now able to automatically root cause these violations and set up aspirational goals to their SLOs and improve reliability over time. We also integrated it with Twine, also known as Tupperware, our container orchestration platform. They allow users to troubleshoot common problems with their jobs, stuck updates, unintended restarts. So now, instead of users going to the Tupperware team, they're able to get automated insights on the Tupperware portal when they come in to look for issues. This significantly reduced the on-call load for the Tupperware team. And last, we built Hawkeye using these foundations. Hawkeye is our AI MLOps tool. As you can imagine, ML investigations can be very complex. When something goes wrong with the prediction, it can be a model issue, it can be a feature issue, it can be a data issue. And it usually took tens of engineers across multiple teams to debug what went wrong. By leveraging Hawkeye using these foundations, we greatly simplified investigations for ML debugging. And with these wide applications, we saw up to a 50% reduction in mean time to recovery for critical alerts when these foundations were used. For Ads Manager case, days-long investigations are now happening in minutes. And we're seeing a really nice adoption in general across on-calls at Meta, with 500,000 automated analysis every week. And not just the numbers. We hear great feedback from our engineers too. How someone is able to prevent an issue to become like a worldwide issue, or how people are able to debug things under 5 minutes. And honestly, we love hearing this more than the numbers. Now, I'm going to hand it off to Madhura to talk about the key learnings that we had along this journey.
Thank you so much, Nitin. It's been super exciting to see the type of impact the team has been having. So along the way of embracing AI ops, we certainly learned a few lessons. And I would like to end this talk by sharing these takeaways with you. First of all, really focusing on improving the quality of the data and metadata of your telemetry systems is key. We highlighted how the lack of correlation around observability data made it super challenging to build effective event ranking solutions. And in fact, even today, we don't have a great solution for service dependency analysis and making upstream and downstream correlations during failures. Secondly, relying solely on automation is good, but it can often result in false positives or missed critical issues. We found that an assistive approach where the AI is generating insights, but these are being further validated by our engineers was often the most effective. Thirdly, it's really crucial to focus on the explainability of your outputs. I highlighted this as I was walking through the event isolation example, but we found that giving our engineers the tools to inspect these results and dig deeper was really important in building trust in the system. And finally, AI ops is definitely not a one-off thing. It requires continuous learning and adapting. We had to constantly evolve our ML algorithms, our investigation workflows, and keep updating our runbooks with constant feedback from on-calls and various teams at Meta. And this was crucial in keeping our system effective with the evolving needs of the company. We are definitely not done yet. There are a lot of exciting opportunities on the horizon with all of the buzz around generative AI and Llama, which is Meta's large language model, and they have a potential to totally disrupt this space. I'm super excited to see where the next leg of our journey takes us. So I hope that this talk provided you with a helpful blueprint for improving your system reliability. And you can check out our blog if you're interested in learning more details. Thank you so much for tuning in.
Thank you, Nitin and Madhura, for shedding light on the evolution and use of AI in running large-scale reliable systems. Now we would like to invite all the speakers for session 1 for a live Q&A. But stay tuned after the discussion when we'll move into the exciting second phase of our agenda, focus on building large-scale systems in production.
Hello, everyone, and welcome you all to our first of 3 Q&A sessions for this year's Winter Systems at Scale. I am Shilpa Lawande, and I will be moderating our Q&A today. We thank you, first of all, to all the speakers for an engaging set of talks, educating us on AI, both scaling multi-tenancy as well as applying it to AI ops. So without much ado, let me get going with the questions. So the first question, let me start with you, Bikash. Can you tell us why you picked inference as the workload for accelerated multi-tenancy?
Sure, Shilpa. Thank you for this interesting question. Let me try to answer it. Inference workloads are characterized by a diverse set of models, which vary both in terms of compute and embedding complexity, as well as the infra resource requirements. These models are also diverse in the sense that they receive varying traffic across regional data centers. Furthermore, inference workload has strict perf requirements in terms of latency as well as throughput. Thus, this low complexity, low resource requirements, and low traffic models aren't always able to fully utilize accelerator resources. In fact, we have seen that sometimes not even a single accelerator device is being fully saturated due to such low footprint inference models. Therefore, multi-tenancy acts as a key infra lever, which provides the capability to further partition and share a single device across multiple co-located inference models. Unlike its counterpart training, which has very different workload characteristics and relatively high resource requirements, a lot of times such fine-grained multi-tenancy support may not provide the same level of benefits as we observe for inference workload.
Great, thank you for that. And a related question to Shao, was GPU sharing for tasks used for training or inference as well in your work?
So for now, the sharing is most targeted for the training workloads because we do not use hardware partition to provide the best isolation. So there's just concern the performance isolation for inference is not good enough. So that's why we primarily target for training workloads.
Interesting. And just continuing the topic a little bit of workloads, you mentioned multi-GPU workloads are harder. Can you talk about a little bit more about?
Sure. So we target for the training, but mostly for the single GPU use case, which is not the traditional multi GPU workloads. We tried for the multi GPU workloads, and because it's super sensitive to any noise. If you had any noise caused either from a noise enable or some sharing, that may cause some cascading side effect in the synchronized training. So for that reason, we do not recommend for the multi GPU workloads training.
Great, thank you. Let me switch to Nitin and Madhura a little bit. Can you talk about how you deal with data-related sort of anomalies like false positives, false negatives, things of that sort? How do you make your tools more accurate over time?
Yeah, thanks, Shilpa. I think that's a great question. So we actually this is obviously a pretty big challenge for all like investigation tools and observability tools. So like everything, we have like a multi-pronged approach for handling some of these issues. And just I think like the biggest takeaway is just having like really solid instrumentation, so we can actually track and observe all of these analysis or investigation workflows that are happening on our AI Ops platform. As we kind of touched upon in the talk, we do have like a very tight loop with some of our highest priority on-call customers, and we kind of get continuous user feedback. So that's clearly like a very strong signal. But beyond that, like we have kind of scaled this out and built like some automated data quality pipelines, so they can kind of just look at critical incidents and root causes that humans who are investigating those incidents labeled, and kind of look back at our automated investigations and see how they match and what like the precision and accuracy sort of looks like there. And we also made it pretty easy for the engineers on our team to easily discover like certain classes of critical incidents and then see how our tools were doing there. Beyond that, like we provide some user-based annotations, so users can come in and say, yeah, we found this to be a conclusive finding or a non-conclusive finding, and kind of just track the overall quality of the AIOps system, and then we can just kind of dive deeper into that.
Got it. So it's basically a continuous feedback loop, both within the tools as well as with all of your user community and all the actual investigations that happen. Great. Okay, next, let me go back to Xiao, and there is an audience question about the cry for help mechanism you mentioned. Can you explain that in a little more detail? Is it basically restarting the task on a dedicated GPU, or is it? Can you explain?
Sure, yeah, I can share more in the details. So when we detect the performance anomaly, we will trigger cry for help. So during cry for help, we will leverage the hardware usage profile of the co-running task to decide if a task is a victim of the resource competition or it's the antagonist in the resource competition. So if it's an antagonist, so that means it's not suitable for future sharing. So we'll opt that out from the sharing. So that job will reschedule running on dedicated GPU. If it's a victim and can potentially continue to participate in sharing, so we'll reschedule to another GPU, and it has the possibility to share the GPU with another job.
Got it. And how do you determine victim and?
Sure. So we leverage some hardware heuristic, and we try to estimate the HBM usage, the memory band usage, and also the compute usage. So it's a blend of hardware matrix that we try to differ. Basically, the more aggressive the task uses the hardware resources, we think it's more likely to be an antagonist.
Got it. Thank you. Hopefully that that answered the audience questions. But folks in the audience, if you're listening, feel free to continue to submit your questions, and we will take as many as we can. Very good. Going back to you, Leon, let me ask you a question. What are the big trade-offs you see between HMT and SMT forms of multi-tenancy? And can you talk a little bit more about the decisions on why you picked one over the other?
Thanks for that question. So the major trade-off between HMT and SMT is that HMT gives us stronger isolation guarantees, while SMT is better at handling workloads with more dynamic utilization. In other words, SMT has potential to give better efficiency, but on cloud infrastructures, isolation is often a crucial characteristics. That's the main reason why HMT is chosen as the GPU multi-tenancy solution for Meta.
And was this specific to Meta? This decision was more closely related to the way Meta's workloads operate, I imagine.
Yeah, it is mostly isolation. So because like we run different workloads, and isolation is a crucial characteristics. We want to protect data, want to protect different workloads from each other. So we choose HMT.
Very good. Going to you, Nitin, let's switch tacks a little bit and say, there are tools, but there are humans who use the tools. I was wondering, is there any resistance you feel from people who actually do these investigations on trusting these tools or using these tools versus using their own instincts or methods to do the investigation?
That's a great question, Shilpa. We did encounter some resistance and a lot of skepticism too, right? There was not just a change to how people did their debugging, but this was a new tech and people had to invest in tuning things when they did not work well. Our key has been strong partnerships. As Mathura said, and I cannot emphasize enough the role of early adopters in this journey. I talk about some of these in our talk, like Web Foundation team, Ads Manager, Instagram Reels. A tight feedback loop with our early adopters went a long way in evolving this for the broader adoption. We were able to identify teams across Meta which would benefit from these solutions by leveraging what their mean time to recovery looked like, and then formed close partnerships with them as well. And once things got more mainstream, people gained more trust, and we were able to quickly scale up with more out-of-the-box solutions.
Great. And can you talk a little bit about going from these early adopters to broader adoption? What were some things you had to do to get that?
Yeah, for sure. So going from a few teams to broad adoption meant we had to make things a lot more easier to use and more out-of-the-box solutions. One thing that worked for us was our focus on making generalizable solutions from the get-go, even though we were working very closely with our partners, few teams, but we had a clear vision on how to invest and make things useful for the general teams at Meta, right? And in addition to the domain-specific tools, we integrate these into widely used observability and alerting tooling. So things were more out of the box for our users. And last but not the least, we leaned on things like in-tool advertising, highlighting where people could use these features to reduce their mean time to recovery, clearly showing the correlations to leveraging these to MTTR, and doing more education also in the bootcamp labs, where every new engineer joining the company is expected to spend the first few weeks learning the new company's tech. So this was useful to have for our new engineers joining the company.
Very good. A similar question to you, Xiao. How do you incentivize your users to adopt GPU sharing?
That's a very good question. So with our first approach, we tried to have a top-down mandate, but it failed miserably, as you can imagine. So instead, we provide incentive as a quota. So let's say the low-power job often get preempted by a high-power job. But we tell them, hey, if you opt into GPU sharing, with one physical unit of GPU, you can submit 2 jobs. So essentially, you double your quota or double your schedulable capacity. So that gives users an incentive. So their manager or director convince their own engineers, if you have a workload that can tolerate this kind of performance sensitivity, and you virtually can sub twice of the job. So that boosts their productivity. Like I said, we try to have the single GPU workloads, which are less sensitive to the performance, and they have just have a small data set to validate their model or configuration. So that eventually boosts their productivity. That got the customer buy-in. So that's the strategy we found out works best.
Great. Very good. Excellent. Let's see. Another question for you. Let's go to Hai. I don't think we've heard from you yet. Talk a bit about, as you productionized the system, what did you notice were the key advantages and disadvantages of multi-tenancy that you found?
Thank you. That's a good question. So there are 3 main key potential advantages of multi-tenancy that we observed. First is better scalability. So because multi-tenancy containers are smaller, so companies can scale up or down container fleet more efficiently to accommodate the real-time traffic. And second is the cost saving or capacity saving that we mentioned in the talk. Is because we can leverage the shared resources in multi-tenancy. Thirdly, this is like specific in our case, we observe lower latency for multi-tenancy containers. So there are two potential disadvantages of multi-tenancy that we don't actually observe during the productionization, but we observe during the implementation. So firstly, if we incorrectly implemented multi-tenancy can lead to security issues as multiple containers now share the same one device resource. Secondly, additional knowledge may be required to set up and use multi-tenancy containers, but we avoid this by because we well documented the setup of multi-tenant environment. And we also see that if the necessary resources are made available to customer, then it can help reduce the knowledge required during the setup process.
Yeah, very good. Thank you. Jen, I think a related question for you. How do the model characteristics impact multi-tenancy choices?
Thanks. That's a very good question. As we can see from the previous presentation that we have in terms of model complexity, which means number of flops per request for this model, and also model size. Our inference models varies a lot across a wide spectrum. And also plus that based on different model architecture, we have different model splits between this host usage and the device usage. So this resource requirement across host and device are also very different based on model structure there. And also the traffic are very diverse, which result in that we have a long tail of very low complexity, very low traffic, and very low utilized models. Because of such diverse resource requirements, one size fits all container size is very suboptimal in our serving world. Therefore, in conclusion, the model characteristic, both in terms of complexity, resource requirement, resource requirement including memory bandwidth, and network utilization. This will help us define a multi-dimensional, multi-tenant container shapes and satisfy the serving workload better. Yeah, that's it.
Thank you. Madhura, back to you. What is your approach to semantically normalized telemetry logs to detect, variety of problems?
Yeah, I think this is a great question. And I think as you touched upon in our presentation as well, sort of just identifying some of these correlations and really working on the data quality were like some of the most challenging problems for us. We did work very closely with like the data science team to really build out like our ML models for ranking these logs. And on top of that, our logging systems themselves do have a bunch of ways in which we can kind of aggregate these semantically. So we have hashes and things like that to represent broader error classes. And again, this was like in very close collaboration with the data science team. And similarly, we have a lot of support for indexing and metadata, which we can add on top of unstructured logs. Some of this is probably also covered under logarithm, which was another log at some point. So those are all of the different factors that really went into build like stronger ranking models for figuring out those patterns.
Great. And just a follow up to you, can you talk a little bit about, you touched upon the idea of an assistive approach versus a fully automated one. Like what might that look like?
Yeah, so this is a great point, and I think we didn't get too much time to cover that in our presentation, but we definitely talk about that a bit more in our blog, so do check that out. But essentially, this is an approach where we kind of go towards more of a decision tree type workflow, where we do automate as much as possible, but then there's a lot of opportunity for the human who's investigating the issue to come in and add more context as they kind of walk through the investigation. And we often found that for more complex problems, this was often like a pretty good approach for making sure that those could kind of be resolved more interactively, where we codify the harder parts, but we also allow users to kind of come in and override context during the critical investigation.
Great, thank you. So, I heard through all your answers, like there's a combination of tech and there's a combination of, people and convincing people to use the tech. So with that, I think we are at time for our Q&A session, for this Q&A session. If there are more questions in the audience that we could not get to, we will try and answer them offline. But look forward to seeing you after an upcoming break. Thank you all to all the speakers for answering all the questions and for the presentations.
Thank you, Shilpa, for the exciting Q&A session and all the speakers from the session 1. We will now move on into the second session of the conference, which is all about immersing ourselves to learn about how to build large-scale systems for actual production workloads. We'll kick off the presentation with Eddie Lee and Brian Fitzpatrick, both from Meta, to talk about Conveyor, the default software deployment infrastructure at Meta. Brace yourselves for the in-depth analysis of Meta's continuous deployment infrastructure, which has been orchestrating over 100,000 deployments per week across millions of machines since 2015. Take it away.
Hey, I'm Eddie. I'm an engineer here at Meta. I'm here to discuss the single deployment engine that we use for the majority of our deployments.
Hey, I'm Brian Fitzpatrick. I'm also a software engineer at Meta. And to set the stage, I wanted to share an interesting story that we feel shows the necessity of Conveyor, which is our single deployment engine. So picture yourself in this scenario. You're a Facebook user in 2014. You head to the site, but it's inaccessible. You see an error page. So what is your first instinct in that scenario? It's call the cops, right? You dial 911. We actually had a number of people call the police because of this outage. We call it call the cops internally when we refer to this outage. This is interesting because 2 months before, the issue that caused it was identified and it was fixed and committed to the repository. But no new deployment took place for 2 months. In general, preventing human mistakes in software deployments at the scale of thousands of engineers is unachievable without unified deployment. So you're going to see how Conveyor's unified deployment system helps resolve these issues. So Eddie, what was going on back in 2014 that led to these issues?
Yeah, well, 10 years ago, deployment at Meta was kind of a mess. We had a lot of bespoke solutions. For instance, our front-end services required a 30,000-line bespoke solution in order to deploy. We couldn't mitigate global outages since each team had their own deployment system, so engineers had to get familiar with the other system before they could really use it. We didn't have a way of blocking diffs during critical periods of the year, where we'd like the services to be a bit more stable and not have new changes pushed. And we didn't have a tool to visualize where deployment was happening, what deployments are happening, and when. So we couldn't really figure out the root cause. And that's what brought us to create Conveyor, the one-tool-fits-all deployment solution at Meta. The first part of this process was to bring new users onto Conveyor by creating Conveyor pipelines. So we had to ensure that Conveyor came batteries included, featuring gradual rollouts, health checks, auto-reverts, and the ability to find flexible pipelines. Gradual rollouts are zero downtime deployments, so we don't have to host a set of parallel machines in order to have a zero downtime deployment through Conveyor. Users just auto-configure it. We have health checks, so during deployments, automatic checks will happen that make sure a job's healthy or not. We have auto-reverts, so, in case a binary just happens to get out there and is bad, we can quickly revert to the previous version and fix things up. And we have the ability to define flexible pipelines where we can handle any artifact and orchestrate it along a graph of actions. As of today, Conveyor has over 35,000 deployment pipelines, and they serve millions of machines. Over 97% of our deployments are now fully automated, so humans don't even have to push a single button to get their packages deployed.
So with a few of the features in mind that Eddie mentioned, we're going to discuss 3 different use cases that have adopted Conveyor as a deployment solution and some of the challenges that we had to resolve for each one. The first use case is FrontFast. So what is FrontFast and why is it a complicated adoption example? It hosts synchronous functions that clients directly invoke. This is similar to something like AWS Lambda. And for efficiency, a single PHP runtime process can execute multiple of these functions concurrently. Tens of thousands of developers commit code to FrontFast, and thousands of commits happen every day. It runs on over 500,000 machines and deploys a new release every 3 hours. So this is a complicated deployment having to deploy pretty frequently. So what does this deployment look like? So it's something like this graph. We have phased deployments. There's 3 pools of machines deployed to in order. The first pool is employee traffic. Next, we proceed to 2% production, and then finally to the remainder of production, 98% of production traffic. And a release will only proceed to the next pool if it has succeeded on the previous pool. You don't want to deploy to production if you deploy to your employees and you already see issues occurring, right? This makes sense. If we zoom in on a specific pool, you can see that there are two parallel checks happening here in this little box. One path of the deployment processes a small amount of traffic using an experimental version of our PHP runtime. The other processes the remaining traffic with a stable runtime. This is to allow us to detect performance regressions or improvements even to see which version we want to continue through using. So now that we know what a deployment looks like, what kinds of features are required from Conveyor in order to support this? In-place updates are integral. Describing your deployment with a directed acyclic graph, which allows us to perform many independent tasks in parallel. Speed is important, obviously, since we're deploying every 3 hours. And the last one is the ability to define what a successful deployment looks like. So going with in-place updates first. So when deploying to a service that is on over 500,000 machines, the standard blue-green deployment is not really an option. Blue-green deployment is where you have a capacity buffer that you deploy to first, and you cut over traffic to serve from that new deployed version. For fast deployments, this buffer has to equal your serving capacity, so you can just do the cutover once. But this means that you need double the capacity to do this. This is not sustainable at scale. You're not going to have a global data center just sitting idle, ready for you to deploy into and switch over. So in-place updates require precise control over individual container updates and the health checks on those containers to ensure the safety of your change. Meta's cluster manager was enhanced to allow updating a specific subset of the jobs container to a new version while keeping the remaining containers on the old version. And it's also integral to allow the service being updated to determine when it's safe to update that container. Our cluster manager's task control interface enables this. FrontFast relies on monitoring health checks, such as the number of fatals, which are 500 errors, the number of unavailable tasks, and the write rate of error logs as a few examples. So if we look at the graph here, you can see during business hours, the request rate goes up. This is production traffic to the site. And our number of task updates that we serve goes down, or deploy goes down. This makes sense because CPU and other hardware resources are being utilized to serve production traffic. We don't want to take that away from production traffic just to deploy an update. But during off-peak hours, you can see the rate of task updates increases to take advantage of more resource utilization. So the second key feature that I mentioned is describing your deployment with a directed acyclic graph. This allows branching and parallel work streams, such as when FrontFast deploys 2 versions to test different PHP runtimes, as we saw in our deployment pipeline earlier. Sequential stages, like those used by previous Conveyor versions, are not generalizable to support these complex use cases, which is why this feature was necessary to unblock adoption of Conveyor for FrontFast. And finally, we are going to discuss customizing success. What does success look like for your deployment? When deploying to many hosts, there's a near certainty of transient issues occurring, either network outages or hardware issues popping up. Pick your poison. We don't want to slow down our 3-hour release cadence just because some RAM went bad or something. We can customize our success criteria to take these expected transient issues into account. So Conveyor allows each pipeline to describe exactly what success looks like for that particular service. So for FrontFast, as long as 90% of updates succeed, we mark this version as deployed, and we can move on to the next release. So now Eddie is going to talk about 3 things that Conveyor needs to support for machine learning model deployments.
Yeah, so I'm going to talk about how we leverage Conveyor's flexibility to orchestrate model deployments through a separation of concerns in our pipelines, tight integration with our testing solutions, and talk a little bit about how we horizontally scale Conveyor to support the higher load that model deployments require. So back in 2014, when Conveyor was created, ML wasn't as hot as it is today. I don't actually know the reasons. I was a freshman in high school, and in software, 9 years is an eternity. But now, about 15,000 of our pipelines are dedicated to model deployments themselves. Luckily, due to the flexibility that we baked into the system, we were actually able to adapt our orchestration engine of Conveyor for ML model deployments. As seen in the diagram to the right here, we have now parent pipelines and child pipelines. The parent pipeline receives a new package and is responsible for testing this package and tagging it to make sure that it's ready for our various stages of production. For instance, it can be a dog fooding, then alpha, then beta, then production. The child pipelines are the listeners to this parent pipeline that are actually responsible for pushing this package out into the world. They will listen to the parent pipeline when it says, hey, this package is ready for dog fooding, and it will actually take the package and push it onto its new jobs. The parent pipeline will then go look at the child pipelines and say, okay, how's traffic doing on these pipelines? Is it good? Is it bad? And if it passes some more tests, it'll then move on to the next stage. Now, that means that Conveyor has to have very tight integration with our testing products. And, well, we do. We run unit tests with our continuous integration before our production binaries are even built. So that's like unit tests or whatever. Then we have integration tests with either predefined parameters or fuzzing options that are run on the production binaries, as well as A/B tests, just to see if we can eke out some performance gains or some performance knowledge on our packages. Finally, we also integrate with our cluster manager, Twine, to perform canaries, where we can push out our production binary to some subsection of the fleet and see how it performs there. Now, ML models are actually pretty interesting to test because unlike most other services, production binaries don't fail during the testing phase, but actually rather during the deployment phase, and usually due to a crash. By separating our ML pipelines into the parent orchestrator, which does the testing, and a child orchestrator, which will do the pushing and then the health checking, we can isolate the issues with our deployment step faster, whether it's unhealthy machines, regional network issues, or even a bad package itself. And despite all the perils of having to constantly push out ML models, we actually are able to make pretty substantial forward progress on them due to 99.9% of all of our deployments through ML being fully automated. We have the confidence that if Conveyor catches something bad, it will revert things before a human has to step in. Now, the interesting thing about ML model deployments is we had to take on a lot more load than Conveyor was initially designed for. We initially attempted to consistently shard the load, so one machine takes on a certain subset of our services, another one does another subset, etc. However, that proved pretty disastrous. If one set of machines just happened to go down one day, suddenly a whole subset of our services couldn't push out new production builds, maybe even for Conveyor itself. Now we have a queue-based system where one worker is in charge of enqueuing items to a queue service, and all of the other workers can take items off that queue. If that main queue loader goes down, we can have other queue loaders pick up from where that first one left off. And this allows us to horizontally scale almost infinitely, since we can just add more workers to do more work. This is elaborated on more in the accompanying blog post to this talk. Now, all these features work great for our models, but what about widely shared code at Meta? Fitz, can you take it away?
Thanks, Eddie. So in contrast to FrontFast that I discussed earlier, another type of service we support are widely deployed binaries and widely deployed libraries. Widely deployed binaries, or WDBs, are CLI tools or daemons running across the Meta fleet. These are distinct because deployment is done on a pull basis rather than a push basis like FrontFast was. Each machine in the fleet periodically downloads the new version of the binary being deployed. But this can take a long time, sometimes more than a week to fully roll out to every machine that needs to get the update. These tools are also used infrequently, meaning health check signal takes longer to collect. If nobody's using your CLI tool and you're monitoring for health check signals, you're not going to get any data. So because of this, some of them have health gathering periods of up to 8 hours. Widely deployed libraries, on the other hand, are common libraries that are used by most, if not all, services across Meta. An example of this is Service Router, which is compiled into nearly every service at Meta. In a monorepo setup like Meta and Google have, changes to a single library like this are compiled into every service that uses it almost immediately. So this means there's a huge potential for widely deployed breakages due to bugs in a single library. So given this potential for high-impact breakages from a single bug in one library, we need a way to block these known bad releases from going out to every service at Meta. And the bad package detector is how we solve this problem. So the way it works is you give it two commit hashes, a blame commit, which is the commit that caused the issue that you're experiencing. The fix commit is the commit which fixes it, as you might guess. With this information, we can then examine every single artifact being deployed through Conveyor and assert that it was built from a commit that is good. If not, we can show a warning and tell the service owner, hey, there's this breakage that is affecting this release. So a good commit is one that is from before the blame commit, or it is from the fix commit and beyond. That makes sense, before the breakage landed or after the fix landed. But just naively blocking based on commit range can lead to unaffected binaries having their release blocked. If my service doesn't include the library that has the bug, I should still be able to release, right? So in order to narrow the scope of impacted services, we also analyze the code dependency graph provided by our build system to ensure that problematic code that was flagged as having an issue or a problem, is being pulled into the binary, is actually being used before blocking its deployment. In order to do this, we have two different components that analyze the dependency graph that you can see on the screen here. The first one runs logic for every change landed into source control, which is what is starting from the right side here. And it computes affected build targets of those changes up to 4 hops away. The second component analyzes each binary, which is on the left side of the graph. It analyzes their dependencies up to 10 hops away, which gives us a total detection range of 14 hops, 4 up from each commit and 10 down from each binary. If they intersect, we know it's impacted by a bad commit and we can safely block the binary. Conveyor runs this validation on every release that comes through the system every minute, just to catch things that pop up whenever they do. And that concludes our use case tour. So Eddie, where does that leave us?
Yeah, so throughout unification, we actually realized some other benefits in how we could monitor and improve deployments, especially when things went south. As mentioned earlier, during the WDB and WDL section, we have BPD, which helps bugs not make it into production. During sensitive periods, like the holidays, we also might just want to limit all code that makes it to production, to only include specially cherry-picked commits, which we can enable through Conveyor's freezes. However, things will go south in production. During situations like that, we can also have a universal kill switch, which will pause globally all deployments that are happening to production. That we can then only spin up production deployments for services that we know are necessary to get the fleet up and running again. Finally, through an integration with Conveyor, we also have a product that allows us to track exactly when revisions enter what regions at Meta, which is very helpful for debugging what went wrong and why. Conveyor, however, wasn't built in a day. We initially started as a rudimentary CLI that would periodically deploy code. Over time, we then added integration with automatic releases through our continuous integration product. Now, that only worked for a subset of packages at Meta, that being 94%. That's great, but that doesn't include our most critical services such as FrontFast, which was mentioned earlier in the presentation, preventing issues such as the ones we laid out, again, in the intro. Getting to 100% consisted of expanding Conveyor to support all artifacts and releases at Meta, where we then were able to realize the emergent benefications of unification, such as with BPD or our universal deployment timeline, Landline. This, again, is expanded on more in the accompanying blog post for this talk. And now, we're deploying with more confidence and less human friction than ever before. Thank you for your time.
Thank you very much, Eddie and Brian, for the illuminating talk on continuous software deployment at Meta. Now let's shift our attention a bit to discuss the design challenges of scaling real-time data access. Please welcome Braden Walker from Figma, who will be unveiling the story behind Live Graph System, built at Figma to provide real-time access to the ever-changing underlying data while seamlessly scaling to the growing user base. Take it away.
Hi, I'm Braden Walker. I'm a software engineer at Figma. Today I'm going to be talking about LiveGraph, a GraphQL-like system designed to make building real-time user interfaces effortless. So I'm going to be talking through a couple of things. So first of all, why LiveGraph, why it exists at all, and what problems it solves. Then about scaling up and the challenges that we ran into, and then a new architecture that we moved to recently and what it affords for us. So for some quick background, if you're not familiar with Figma, it's a platform for teams to build products together. Now, this is really important to us. We want people to be able to collaborate and work together because we think better things are built together. So let's talk through a few things. First up, why LiveGraph exists at all and what we needed it for. So real-time collaboration is really important to us. This is everywhere in the product. We want it to work the same way alone as it does together. We want collaboration to feel effortless and natural. We need this to permeate the entire product surface. So we don't want this just to be within files, but everywhere within the product so that it feels alive. And latency is noticeable in this environment because you're generally collaborating with people that you're actively talking to. You might be in a meeting together, and so we need the system to move at the same speed that human communication does. So this totally rules out technical solutions like polling. We could never keep up. So life before LiveGraph. The way this tended to work is that when a product engineer was building a new product surface, they would handwrite an endpoint on the back end to deliver all of the data that they needed to display on that surface. Then, in order to add real time, they would explicitly add publishes and subscribes through a pub subsystem. So there were channels of events, and the back end had to figure out what to publish and when to show to the clients. Now, this had all of the problems that you might expect. So for one, it's cumbersome at development time because it's extra work to do. And so that effort would sometimes get delayed, sometimes would move to a fast follow for a product. And so the product surfaces would generally feel alive, but sometimes they wouldn't. We also had problems with missed events. It was easy to forget to publish something or forget to subscribe, for the client or server to disagree about where a particular event was supposed to go. And it was really difficult to debug. When something went wrong, because the cause and effect were so separate, it was really difficult to figure out what happened. So enter LiveGraph to solve a lot of these problems. It gets its name and its inspiration and a lot of its general workings from the same place as GraphQL, and it works in a very similar way. So we have sort of three things that the product engineers interact with. So one is an object graph. These are the data types and their relationships with each other. Then we have GraphQL queries where the UI can ask for the data that it needs, which might traverse those relationships as necessary. And then, and here's where the magic comes in from LiveGraph, React hooks. So instead of just asking for the results of a query, you subscribe to the results. And as things change on the server, we magically deliver those updates down to the UI. The UI gets new state and re-renders automatically. So I'm going to talk through each one of these things a little bit. So the object graph, here's a tiny little slice of what the object graph looks like. So we have files. Files have several comments. Each comment has an author. The author is a user that has a name and a thumbnail URL. Comments also get reactions because people can leave behind thumbs up or smiley faces. And those in turn also have authors. So if we want to render a UI that looks like this thing on the right, where we have a comments pane that says, you know, all of the contents of the comments, but also the users that posted them, their thumbnails, all of this sort of stuff, we have a GraphQL looking query on the left there that says, for this given file, give me all of the comments in it. For each comment, give me the message that created that. For the user that posted the comment, I need their name and their thumbnail URL, and I need all of the reactions underneath so that I can draw them on screen. And the way this actually looks in the UI code is we write React components that know how to render out UI. But the way they connect with LiveGraph is with this use subscription call. So this single line means fetch me the results of that query, but also keep it up to date. And so LiveGraph knows how to watch for the changes that that query might need to see and notifies the client, and the client knows to re-render with the new state. So this one line of code is all it takes to make this comments pane real time. As people are posting new comments or posting new reactions, it will automatically update. All right, so I'm going to talk about scaling up. First, in order to do that, we'll talk a little bit about how LiveGraph works, and then we'll come to some of the challenges that we ran into doing this. So at the most basic level, this is LiveGraph's architecture. So we have clients that are mostly web browsers talking to LiveGraph, the server. They keep open a persistent WebSocket connection, and they send over the queries that they want to subscribe to. Now, LiveGraph takes those GraphQL queries and breaks them into individual database queries to fetch the objects that are needed. It asks the database for the results of those queries, it caches the results in a query cache, and then we watch the replication stream from the database so we can see every mutation that's happening to all the data and mutate the query results as they change based on those mutations and notify the clients when they have changed. Now, I'm using query to talk about two different things. One is the GraphQL query, which is the traversal of the object graph that the product engineers write in the client, but these individual database queries are what I'm mostly going to be referring to for the rest of the talk when I talk about queries. Now, let's talk about what it takes to scale this thing up. And there are a few scaling dimensions to pay attention to. One is that more product surfaces are using LiveGraph as their backend, both because we're building new things and because we're converting existing things to use LiveGraph. The complexity of those surfaces increases over time because users use those features, right? As time goes on, we have folders with more and more files in them because users are using it. And then Figma itself is growing overall. So we're acquiring new users and we need to worry about that. All right, so let's talk about some challenges. And one of them is that as we're getting more traffic, we need to add more client machines, which means naturally we add more LiveGraph servers to keep up with them. Now this has a couple of problems. One of them is that we have to fan out all mutations to all LiveGraphs. We don't know which LiveGraph is interested in which parts of the database mutating because LiveGraph itself is in charge of keeping track of that. So we have to send all mutations to everyone. Two, the caches are fragmented. So we have query caches that live inside each one of these nodes. And because Figma is inherently a collaborative product, right? You might be collaborating with somebody else on the same content, but you're probably talking to separate LiveGraph servers. And so you're not likely to hit a warm cache. And three, and perhaps most important, we have to fan in all of the mutations to a single LiveGraph machine, and it has to process all of them. Because we don't know which LiveGraphs are interested in what, each individual LiveGraph has to process mutations to all databases at Figma. And as we're scaling up, we're adding more databases, we're serving more writes, there are more mutations to process. So this is existential because eventually one machine won't be able to get through all of this. So this led us to trying to build a new architecture. So I'm going to talk through a couple of things on this point. The requirements that we needed to fulfill, an idea that seemed sort of obvious at first, but we ended up discarding for a few reasons, some observations we came to in doing that, and then the three-tier architecture that we ended up with and how it works. So the existential requirements, on top of everything that LiveGraph already needs to be, it's the surface that the product engineers interact with. Of course, we need to deliver things with low latency. But as we're scaling up, these are the things that we're worried about. One, we need to be able to consume sharded database mutations. So as we're adding more databases, we need to not have a single node processing all of the changes. We need to process only a slice of them at a time. Two, we need to centralize and share the cache. This means that we can get better bang for our buck out of fewer resources. And three, we need to be able to scale this thing out as traffic increases, as usage increases, as complexity increases. We need to be able to add more hardware without increasing the fan in or fan out along with the scale of Figma. All right, so let's talk about an idea for solving this problem. And we're revisiting this sort of architecture diagram here. So we have multiple database shards and they each deliver all of the mutations to both of the LiveGraphs here. Now, as we're scaling up, we're adding database shards. And you might think that because we're already sharding the databases, we may as well shard LiveGraph the same way. So we split the query cache out from LiveGraph and have each one mapped to a single database shard. Now, there are a couple of problems here. One is that we need LiveGraph to be intimately aware of the topology of the databases underneath, the placement of data across those shards. Two, we need to be able to execute queries both forwards and backwards, right? Across many database shards. A single query might not be homed on a single database shard, which means we have to fan out to the query caches that own fragments of that data and then be able to merge those results together into final queries and have real-time changes flowing the other direction, updating those things through that execution engine. This is all really complicated. And three, most importantly, this would mean that we are rather intimately tied when the sharding changes. So we need to be part of the process by which we move data around among nodes at Figma. And this is already a relatively delicate operation that has a lot of steps to it, and we don't want LiveGraph to have to be that intertwined with that process. So we ended up discarding this idea. But we observed a few key things about the way the system works. One is that the query shapes are known basically ahead of time. Now, the actual queries done against LiveGraph are written down in source code. They're committed by the product engineers working with LiveGraph. And so they change at about a human scale. They change day to day. They don't change second to second. 2, the queries are mostly simple. So we already have this enforcement from LiveGraph that queries can't have things like joins or sub-expressions, anything like that. They're basically all straightforward select wheres. Sometimes the filter expressions get kind of gnarly, but in general, they're straightforward queries. And then 3, reads are much more common than writes. So this is important because the previous system focused a lot on making mutations and applying them to query results very, very efficient. But we can actually afford to do something slightly suboptimal here in order to simplify the system, which we'll see in a second. All right, so this is a diagram of the 3-tier architecture that we ended up landing on. It's not going to be immediately obvious how this leverages the observations that we just talked over and how it solves the problems that we went through. But I'm going to talk through each one of these components in a second, and we'll see how at the end it all comes together to solve those problems. But at a high level, this is the general concept. So the important thing is that we have caches in the middle. These are cache results of individual queries. So the cache keys are SQL queries, the cache results are rows. Then, in order to keep that cache up to date, we have invalidators that are responsible for consuming the stream of mutations from databases and then emitting the cache keys that need to be invalidated. And then we have front ends that sit on top, and these are in charge of taking GraphQL queries and expanding them into database queries. When it receives an end validation for a query to say that the results may be out of date, all it does is requery. So this helps us avoid the complicated query engine edge that LiveGraph might have gotten into. All right, let's go through each one of these things. So we'll talk about how we generate invalidations. This is important for how we are able to consume database mutations in a sharded way. So we have these shapes that are written into source, like the thing at the top there, right? This is the file shape, which it fetches information about a particular file given its ID. So in a shape, all of the arguments are templated out. And an actual query is a shape plus the arguments that go into the query. So the mutations that we consume from the database look like this thing just below the shape, where we have a pre-state and a post-state. We get to see the state of a row before the mutation and then what the row looked like after the mutation. So this particular mutation is a rename, right? Someone changed the name of this file. And so we have to figure out which query needs to be invalidated. Now, given the shape file, we can figure out that the one that needs to be invalidated is the one with the ID that is this file. This is rather straightforward. Here's a slightly more complicated case. So we have a query shape that is responsible for fetching the files in a particular folder. So the argument is the folder ID. We want to return all the files that are in that folder. If we have a mutation like this that changes which folder the file is in, right? This is a move from one folder to another. We need to invalidate both the query that fetched the contents of the folder that it used to be in, because we need to see it disappear from where it used to be, and invalidate the query for the folder that it is currently in, because we need to see it appear where it's going. And here's a slightly more complicated case. Now, this query fetches recent drafts. So we use it on a particular folder to fetch files that have been changed recently, say in the last 7 days. So when we get a mutation that changes the updated at of a particular file, we need to figure out which queries need to be invalidated. Now, it's obvious that we need to template in the folder ID that the file is in, but it's not clear what we need to template in for the updated at, right? Because any query that is looking for an updated at that's older than either of these timestamps might be invalidated by this. So what we do is we cheat and we invalidate all of them. It turns out that this is super effective in practice because, generally speaking, the rest of the query that we can template in is selective enough that the over invalidations are not terribly expensive. And 2, because mutations are not that common relative to reads, remember, we can afford to do extra requeries when the results of the query did not actually change. All right, so we've shown that the invalidator is capable of generating cache key invalidations from just a single row mutation, which means we can trivially shard the invalidators. We can have them each consume just from one database shard and generate cache key invalidations from just that shard. Now, this sort of sounds like something from the previous design that we ended up objecting to, but it's different in a fundamental way. Because the invalidators are just working on single row mutations and don't need to know any other state, they don't need to care where the data is actually homed. And so they don't need to participate in any sort of resharding process, moving data from one place to another. They just look at mutations and generate invalidations. So this means we're not actually intimately tied with the database shards. We need to know what shards there are, but not any information about what lives where. Now, it kind of looks like we've got the same fan-in problem, just one step deeper. So let's keep moving here. So we take the caches and we also shard them, but we shard them by a hash of the query. So we take the entire query, the shape plus its arguments, and we hash them together to figure out which cache node is responsible for a query. Now, when an invalidator generates a cache key invalidation, it can also hash that invalidation and send it directly to the cache that's interested in it. So even though we have the same number of arrows between the invalidator and the cache that we previously objected to, each one of these arrows is actually carrying much less data because it's only the stuff that we know the cache is already interested in. Now, in order to prevent the fan out of those queries where we had to invalidate all arguments, we actually template out the arguments that we can't invalidate directly. So in the case where we had that recent drafts shape and we can't template in the updated at invalidation time, we also route all of those queries to the same node. So we sub in a star and hash that to figure out which cache node to send it to, so that we only have to send the invalidation to one node, even though it might invalidate multiple queries that are living on that cache node. And the next step is adding front ends. So as we're scaling up, we're adding front ends to serve more user traffic. And in order to deal with this, we need a way of routing invalidations from caches to the front ends that are actually interested in them. And the thing that we use to do this are probabilistic filters. So these filters are allowed to say, for this query, is this front end interested in it? And sometimes it will answer yes, even if the front end isn't actually interested in it, but at a low rate. But they will never answer no if the front end actually is interested in them. But they have this advantage that they're extremely small relative to the amount of information that they carry, which means they're very easy to move around the network as caches deploy, as front ends reconnect to caches, and they're very efficient to search through. All right, so we've seen here how we can shard each one of these pieces and solve all of the fan-in and fan-out problems that we had from before. So the invalidators are only consuming from a single database shard. When they generate an invalidation, they know to route the cache key to only the cache node that is actually interested in it. So we don't have any fan-in at the cache nodes. And then the cache nodes know how to route invalidations only to the front ends that are actually interested in those queries using the probabilistic filters. And then when the front ends see that a query that they're interested in is invalidated, they just requery. So this helped us simplify greatly what LiveGraph's relationship with the database is. We just look at queries, we send them along when we need to. We never have to interpret them or mutate query results as changes come in. We just requery. All right, some conclusions. So LiveGraph can scale horizontally to keep up with Figma scale. As we're adding more users, we can add more machines. As we're adding more database machines, we add more invalidators. As we add more traffic, we can add more cache shards. And as we're adding users, adding clients, we can add more front ends. The mostly static query shapes and the three-tier architecture are what helped us to do that. And then third, sharing the cache, moving it out, centralizing it, gave us much better cache effectiveness, so we can get better performance at a higher cache hit rate for much lower cost. I want to talk a little bit about the future work that we're taking on following this project. So one of the big things is that we want to bring the same effortless real-time to server-side computation that we have for objects that are directly delivered out of the database. So we've mostly been talking about objects in the object graph that are selected just by database queries, but not all of them are that way. We have different amounts of server-side computation for different use cases. For example, you might have old clients that you want to maintain compatibility with. You're adding rich text to a field, and you need to be able to still deliver the plain text that those old clients are looking for. And we have several different features that do this of varying level of complexity and power, but the most powerful of them requires a bunch of handwritten stuff, just like the pre-LiveGraph days where we have pub subs to deliver invalidations back to LiveGraph. We have some ideas for how to do this really well so that we have the same effortless real-time with server-side computation involved. We need to improve our telemetry and developer experience. So it's really difficult to understand with all the complexity that's happening inside of LiveGraph, what is happening when rendering UI and why. And so we want to improve our tools to help developers work better with LiveGraph. And then third, this new architecture helped open the door to increasing efficiency and lowering cost. So we have a few options on the table for further reducing cost of LiveGraph that we'll be exploring next year. Thank you so much for listening. And thank you so much to this wonderful, talented team of people. My information is here if you'd like to get in touch. And of course, Figma is hiring if this sounds interesting and you'd like to come work with us. Get in touch. Thank you.
Thank you, Braden, for that engaging presentation. Next, we will explore the synergy between asynchronous computing and data streams at Meta. Say hello to Sayak Kundu and Omar Abdu as they present bringing data to asynchronous computing at scale. They will be sharing their insights into the technical challenges and strategies employed to scale the data transport layer at Meta to handle trillions of daily jobs across thousands of heterogeneous tenants. Take it away.
Hello everyone, welcome to our talk. Today we are going to talk about bringing data to our asynchronous computing platform over here at Meta. I am Sayak Kundu, a software engineer on the serverless computing team over here, and I'll be joined by my friend and colleague Omar Abdu, who's also an engineer on this same team. So the scaling challenges that we'll be exploring today are pertaining to the data transport layer of our platform. This is responsible for moving multi-trillion workloads per day, which amounts to more than petabytes of information. These workloads are responsible for powering some of the very popular use cases across Meta that we'll look into. For the agenda, we'll start off with a brief introduction to asynchronous computing. From there, we'll deep dive into some of the scaling challenges that we want to talk about, and then we'll wrap it up with the learnings. So the serverless computing platform that we have here at Meta is responsible for powering use cases across apps like Instagram, Facebook, WhatsApp, or Oculus, and also Threads. There are trillions of daily asynchronous computing requests which are running. We have a footprint of more than 100,000 servers globally, and all of this is catering to use cases pertaining to 3 billion plus daily active users. One of the use cases that you might be familiar with, which is powered by our platform, is the birthday notifications that you get on Facebook. Now let us understand what asynchronous computing is. It's a paradigm where the user is not waiting for the execution to complete for the functions that they are scheduling. The execution completes within an agreed upon SLA with the user. The advantage of this is the user does not need to block their latency critical operations on the completion of some computation which can be offloaded to a later point of time. By executing functions off-peak, we obviously get better utilization of our resources, which promotes efficiency. At Meta, we have this platform where users across the different engineering teams can run their asynchronous computing functions. We take care of the scalability of the scaling and provisioning needs, and this promotes developer productivity on their end because they have to worry about lesser number of things. Worth mentioning, because we have this central platform, we can also focus our reliability initiatives over here, which also promotes reliability of the overall system. We already have a couple of blogs on our engineering website where we discuss more about this platform and the different use cases it powers. We won't be going over these in detail today, but instead we will be looking at how we are bringing data to this asynchronous computing platform that we have. As you can see on the screen, initially when we started off, we had a client library which the users would use to push data into our platform. Eventually, we realized that we would want to expand further and develop integration with other data sources like streams or data warehouses, from where we would pull data and would schedule them for execution. The users can declaratively thus run their functions on our platform. With this expansion, we naturally encountered more scale and more challenges, and that is where we will deep dive in the subsequent slides with Omar. Off to you, Omar.
Thanks, Sayak. Now that you're familiar with what our platform provides, let's look into some of the scaling challenges we solved. What are the factors that brought those challenges to the transport layer? As the platform evolved, the system went from serving a handful of use cases to thousands of them, and executing trillions of items per day. Different tenants have different types of workloads. Workload patterns can be extremely unpredictable, with spikes of executions, different data sizes, and sudden compute failures. How do we make sure the system can handle those different scenarios with good resource utilization? We believe these challenges and techniques to address them are shared in lots of multi-tenant systems. Let's explore some of them. We'll first look into the multi-tenancy problem that arises and how we solve that using sharding techniques. Second, we'll look into how do we think about allocating resources from the transport layer to different tenants according to their needs. Third, how does the system react to downstream failures such that a graceful behavior is maintained? Let's take a deeper look into the asynchronous computing platform. The system has three high-level blocks. On the left-hand side, we have the data sources, which house the data that will need to be passed through the user functions. On the right-hand side, we have the compute, which is in the environment where user functions are executed. In the middle, we have the transport layer, which is responsible for pulling data from data sources and sending them to execution to the compute layer. It also checkpoints progresses as it goes. The transport layer ensures executions are happening with high throughput and low latency. The transport layer will be the focus of our talk going forward. At any given point in time, the transport layer is moving workloads for thousands of tenants, which are all sharing the same resources. In an ideal scenario, the transport layer is able to reliably serve all tenants, and everyone gets just what they need. However, in an environment where we have thousands of tenants, we know that not all of them behave the same. Due to a spike in execution rate, compute availability, or a change in data patterns, some tenants would demand more resources. Unsolved, we start seeing the pattern of noisy neighbors. In this example, the green tenant took over resources which hindered the progress of the blue and yellow tenants. This can't always be addressed by adding in more capacity. Even with horizontal scaling, the same pattern can still repeat. Let's start looking into how we thought about solving that problem. The core idea for addressing the multi-tenancy problem is thinking of the transport layer as units, where each unit is responsible for serving a subset of the workloads for a specific tenant. We call units a shard. The union of all shards would then form the whole transport layer. We can then reason about how to isolate between those shards such that each tenant gets what they need without interference from others, and how many of them do we need per tenant. Let's look at both those aspects next. The transport layer is comprised of several containers. One method of isolation is to host a shard on each container. This is straightforward, since we can easily reason about resource protection in this setup, as there is no in-process sharing between shards. However, due to the same reason, fragmentation prevents good capacity utilization, which results in a more expensive setup. Provisioning new containers is also a relatively slow operation compared to what we'll discuss next. Instead of hard isolation, where there's one-to-one mapping between containers and shards, we can host different shards on the same container, but this time with logically imposed resource boundaries. In this mode, there is more emphasis on resource protection within the process. This ensures liveness of all shards, but it also introduces additional complexity on the application layer. Stacking shards this way allows us to be more efficient, as we don't need to pay the tax for each container whenever we add a new shard. Additionally, provisioning in this method can be much faster, as processes are always up and ready to host more shards. Let's dive deeper into how to apply this pattern on the transport service. Essentially, we need to allocate a specific number of shards for each tenant, and the system needs to consistently respect that. You may be asking, how do we choose the number of shards per tenant? Sayak will cover this soon. One thing we want from the system is to be fault tolerant. In this example, we see that container 3 went down. What we'd like to see is the shards hosted by container 3 are moved to some of the other healthy tasks. In this example, the green and the blue shards move to task 1 and 2. Another thing we'd like to see is even distribution of shards. In this example, shards are skewed to task 1. However, a more optimal distribution would be moving the pink shards to task 2 and 3. To satisfy requirements such as fault tolerance, load balancing, and auto-scaling, which Sayak will speak about, we realized that a global view is needed. Shard Manager is a shard management framework which consistently watches the transport layer and applies our intent through shard assignment commands. This happens in cooperation with the transport service tasks. If you're interested about Shard Manager, feel free to check out our blog on the Meta Engineering website. Thanks for listening so far. I hand over to my colleague Sayak to speak about resource provisioning. Precisely, how many shards do we allocate to each tenant?
All right. Thank you, Omar. So now that we have understood how we are solving the multi-tenancy problem by breaking down the transport service into shards, we will look into how we are going to allocate these different shards to supporting the workload of different tenants. This we'll explore as the resource provisioning chapter of our talk. Now, why is this relevant? Let's understand that. After our product or platform became generally available for the engineers across different teams at Meta, they could onboard onto it independently. This meant that it was very hard to predict the workload volume. Secondly, even with an existing set of users, their workload volume could also vary based on their usage pattern or even just the function running time. All this together summed up to be a very non-deterministic workload volume that we had to deal with in our transport service. On the graph that you have on the slide, we have tried to represent the workload volume from a specific tenant, and you see that across time it is spiking up, then it is again settling down a bit, and it does not follow any regular pattern. One solution, of course, is over-provisioning our entire tier such that we are able to accommodate some kind of predefined peak. But however, that would mean that there's significant wastage across all the troughs. So it was not an option. Now, being an asynchronous computing platform, we had the flexibility of adopting a reactive autoscaling strategy. Let's understand what this is. Across our tier, we are emitting from the transport service many load signals. We would try to have a global view of these load signals and collect it and try to take some autoscaling decision based on these load signals. After we have taken these autoscaling decisions, which will probably tell us to either scale up or scale down, we will execute it and in the process come up with new set of shards. We will then allocate these different shards to the workload for different tenants. This we term as resharding. However, coming up with a very reliable or accurate autoscaling decision is a very hard problem, and we tried some ideas which we'll explore in the next slides. Our transport service at any point of time would contain in-memory buffers which are accommodating the workload items that has been pulled from the data source and are supposed to be sent for execution in the compute layer. These items we will term as the ready items that you can see on the diagram. There's also a second variety of items which are represented as in-flight items. These in-flight items are items for which the RPC has already been initiated, but we are awaiting success or failure of those RPCs. The connection with the compute is still open. We need to keep track of this and can't do a fire and forget, because in case if the execution fails or the RPC fails, then in that case we need to retry them. If we don't retry, then there would be data loss, which we can't accept. Hence, at any point of time, our in-memory buffers in the transport service would have a mix of ready items as well as in-flight items. If at any point of time the compute is not able to take any more RPCs, then it will express back pressure signal to us in the form of throttling exceptions. Thus, what we found was at any point of time, if there's a lot of in-flight items, that can be taken as a hint that the compute has not expressed the back pressure signals or the throttling exceptions yet. This means that maybe we can even throw more RPCs to the downstream or the compute layer. We take this chance and we scale up our tier to parallelize the flow to have more RPCs. The converse is also true. At any point of time, if we see that there are a lot of ready items but very few in-flight items, we understand that the compute probably has already expressed some back pressure signals, which has resulted in this state. So parallelizing the flow or scaling up the tier to parallelize the flow does not make sense. In such an instant, we try to scale down to reduce the flow. However, the load metrics that I have been talking about so far are extremely unstable. Hence, if we are considering a snapshot of the load metrics at a point in time and taking our auto-scaling decision on basis of it, it will be extremely conflicting. If we are acting on these auto-scaling decisions, then it would lead to us scaling up and down continuously, which will also make us waste a lot of time resharding. This is obviously not optimal, and we would end up spending a lot of time as well as resources. We try to mitigate this concern by looking at a rolling window average. Hence, on the diagram on the slide, you see that there's a look back window across which we will be monitoring load signals, and we will be acting upon a decision based on the load signals throughout this window. However, this also means that our tier auto-scaling would be a bit less responsive. And we have already mentioned that our workloads tend to be extremely spiky. So in order to mitigate this, we try to also over-provision our tier a bit such that we can accommodate this spikiness. Alright, so now we have gotten some idea of how we are breaking up the transport layer into the transport service into shards and allocating different shards to different workloads. We will now come to some of the nuances we need to keep in mind while firing the RPCs to the downstream. Our transport service at any point of time, as we have already learned, is pulling data from data source and RPCing it to the compute layer. The compute hence is the downstream for us. How do we manage our RPCs such that the downstream is healthy is the topic of this final chapter of our talk. We term it as downstream protection. Also worth noting that any system architecture which has a similar mechanism of pulling data from point A and RPCing it to point B would be able to leverage some of these ideas that we'll be exploring in the subsequent slides. So the lag in the data source is when workloads are getting generated, but they are not getting picked up immediately. In an ideal case, we would want to minimize lag, which means that we would try to pick up workloads as soon as they are getting generated or made available on the data source, provided the compute still has the capacity to execute those workloads. We have already learned from our auto-scaling section or resource provisioning section of the talk that in these scenarios, we will try to scale up the tier in order to minimize lag. The ideal state is zero lag. Items or workloads are getting generated and instantly are getting picked up and sent for compute. This is the ideal state. But however, in most of the cases, as we scale up in pursuit of this ideal state, we are usually limited by the compute layer. This can be because of capacity constraints in the compute layer. The function running time for the user's workload might increase, or there can be some other bug in the function code which causes some regression. In either of these cases, the downstream or the compute layer would try to express some back pressure signal to the transport layer by erroring out requests and throwing throttling exceptions. So in such a scenario where we are experiencing errors or back pressure signals from the compute layer, we want to reduce the flow by also reducing ingestion from the data source. At the same time, after this has happened, we have a handful of RPCs which we initially tried but has been errored out. We can't drop these requests or RPCs because that would lead to data loss. Hence, we need to retry it again. But we need to carefully do this because if we are retrying too aggressively without considering the situation of the downstream, it can overload the downstream, and if there's a degradation event, it can just lead to a cascading failure. So we need to do these retries gracefully. Lastly, as we already spoke about that, we will be reducing the ingestion flow. Eventually, the downstream would be reviving because we are retrying gracefully and we are allowing it the time for reviving itself. When the downstream has recovered, we would again want to eventually increase the flow because otherwise we would not be tapping full potential of the compute layer. So all of these aspects are combined into a strategy by which we maintain the flow of the RPCs from transport service to downstream or compute layer, and we term this as our flow control. The strategy of how we do this entire thing is what I'm terming as flow control over here. So for our flow control strategy, it was very hard to come up with static parameters because these kind of degradation incidents are highly non-deterministic. We thought that we would come up with an adaptive strategy where we have some kind of feedback mechanism from the downstream such that we dynamically adapt our flow from transport to the compute layer. This is what we will understand now. We modeled our adaptive flow control strategy on a system of budget of tokens, where let's assume that one RPC would ideally wait for one token, and once the token is available, then it would consume the token to initiate the RPC to the downstream. If the RPC was successfully completed, then the token would be replenished back onto the initial budget or the pool of tokens. As this would go over time and we see gradually a lot of requests or RPCs succeeding from the compute layer, we would take that as an indicator of a healthy downstream. Consequently, we will also want to then gradually increase the budget. However, there might be a time when we see exceptions are starting to happen. This is downstream conveying us some kind of back pressure. If we see this happening, we want to decrease the load. We decrease the budget of these tokens very rapidly. Decreasing this rapidly is important over here because degradation incidents can happen really fast, and unless we decrease the load, it can lead to a cascading failure. So by decreasing the budget, we are also constricting the flow, and over time our hope is that this will allow the downstream its time for recovery. As the downstream recovers, it will manifest in more and more requests succeeding. Then we will eventually again increase the flow. This kind of forms a service cycle where we are constantly getting feedback from downstream and modeling our flow based on that. This dynamic balance of workloads across the transport layer to the compute is the essence of our flow control logic. For more details, we actually employ this algorithm called AIMD, which stands for additive increase and multiplicative decrease, for maintaining our budgets. All right, and with that, I'll hand it off to Omar to cover the concluding section of the talk. Omar, off to you.
Thanks, Sayak. Okay, let's recap on what we discussed today. You first covered the multi-tenancy problem that arises when we have thousands of tenants sharing the system, and how did we protect the system and tenants from each other through sharding techniques. We also discussed auto-scaling techniques to adjust to varying workloads, precisely how many resources do we assign to each tenant. And we finally closed by some downstream protection techniques to ensure the system behaves gracefully in the midst of failures. Let's look at some learnings from this journey. Even when starting with a small number of use cases, baking the tenant concept early on in different layers of the stack, such as provisioning, capacity management, even alerts, enabled the refinement of the system to scale to much more tenants later on with a solid isolation story. Another learning we extracted is lots of the problems we were working on were optimization problems. How do we scale different tenants? How do we protect different tenants from interfering with each other? For us engineers, it's a natural tendency to optimize as much as possible. However, we found out that it's always a good idea to speak with the customers and align with their expectations and encode them into SLAs. This enables us to take informed trade-offs between performance, system complexity, capacity usage, and even operability of the system. Thank you so much for watching the talk. We also have a blog on the Meta Engineering website. Feel free to check it out.
A big thank you to Sayak and Omar for the insightful journey in the world of building a multi-tenant transport layer to bridge the compute with Meta's heterogeneous data stream. Building on this theme, our next talk covers the various intricacies and complexities involved in building systems to manage data lineage and restatements in the enterprise world. Please join me in welcoming our next speaker, Jack Pulicotal from Microsoft, who will be presenting Data Lineage Unleashed, Nitro's approach to automatic restatements. Take it away.
Hi, my name is Jack Pulicotal. I'm the engineering architect for a central data team in Microsoft called Ideas. One of the many things we do on the team is curate interesting data points for public dissemination, the kind of data that makes the news. We call this data workload non-financial disclosures, as they are primarily oriented for messaging aspects of business health, supporting the product brands, or demonstrating thought leadership in a specific domain that the company is investing in. But it goes beyond that. Data points and insights like these shape just about every aspect of decision-making and operations in a modern enterprise like Microsoft. Today, I'm going to take you behind the scenes to talk about how Ideas sources such data and explain a unique set of challenges that come with it when we attempt to do this at scale. Through this talk, using Ideas as an example, I'll touch upon how the flow of data in large enterprises can develop complex data lineage. We'll see how such complex lineage poses a challenge from a data integrity perspective, driving the need for data restatements. We'll then get into how automatic restatements are supported in a system called Nitro, and some of the lessons we've learned along the way. Let's get started by going back to how Ideas sources the type of data we just talked about. Ideas is what we in the data business call a source of truth data aggregator. Today, the team aggregates from over 2,000 sources, everything from product telemetry, Microsoft internal repositories, and external sources. Data is then transformed into a set of curated assets that are considered authoritative. And this data is then used for a variety of workloads that go well beyond non-financial disclosures. From business metrics for high-level decision-making, metrics used for computing compensation, product experimentation, paid media analytics, personalization, sustainability efforts, supporting data for research studies, as well as data products that power different external-facing views, and product behaviors, like system thresholds for fighting email spam. This data is also shared with the right privacy and compliance controls to hundreds of data teams in the company. Now, this was not always the case. Over 6 years ago, this team did not exist. For the most part, data was independently sourced by consumers from different data providers. There was, and in some ways continues to be, considerable heterogeneity in the way product teams in Microsoft make engineering choices. And this extends to how they do telemetry and data. So as you can imagine, a question would frequently have multiple answers depending on which sources were used and how they were computed and by whom. This isn't a problem unique to Microsoft, but the sheer size of the organization, the breadth of the product portfolio, and the range of business models supported by these product teams, and the markets in which they operate, all make it very challenging to get one version of the truth that different parts of the company could work with. This frustration was one of the core reasons why Ideas was born. Now, this kind of transformation will inevitably be complex. Just how complex? What we're looking at is a directed dependency graph that represents this transformation from a snapshot that was taken just last week. Each node in the graph is either a dataset or a data interface or some activity that transforms data in some way. Every directed edge reflects a dependency between them. This lineage graph has over 80,000 nodes and 120,000 edges. This is what it takes to connect those 2,000 sources from across the company to support the data workloads we just discussed. A couple of other interesting things about this graph. A significant majority of datasets here are partitioned by date. And most activities choose which specific partitions they read and write from every time they run. This is not rendered in this visual, but it's a key detail, and we'll discuss why it's pertinent. The graph itself is fast churning, with two continuous forces causing this churn. The first is on account of data providers, new data sources or changes to data sources, new products and feature releases, system migrations, etc. The second is on account of data consumers, new use cases, new scenarios, new questions from leadership. This translates to over 1,000 deployments each month that can impact lineage. Finally, this lineage graph is not owned and operated by one group of people. Somewhere close to 400 developers across the company own and operate these pipelines, a good number of them within ideas. Activities run in pipelines, and pipelines are organized and hosted in data factories managed by Azure Data Factory. Every colored box represents one such data factory, and the color identifies a unique incident management group. Such groups are used by engineering crews so that monitoring alerts can be directed to the right team. With a federated and fast-moving lineage graph like this one, it is possible that bad data is introduced somewhere in the graph. It can be on account of a bug. It can be an uncommunicated change from a data provider. For instance, there is a migration or some major refactoring in the data provider's code that had an unanticipated change in the data that's flowing to consumers. When this happens, it can be a while before it is discovered. Hours, days, even months. Often, it's discovered several layers downstream from the source, when the end users of the data notice a shift in the distribution of an aggregation. What happens when we run into such an issue? As a source of truth data aggregator, how do we deal with it? To illustrate the challenge, look at this close-up section of the lineage graph from our Azure Purview data catalog around a specific data interface. Say that we have a repairable data issue on the data set highlighted in the red. Once fixed, we need a way to replay all the computational layers that are derived from it, everything that is highlighted in yellow. That is what is called a data restatement. We fix one or more data sets and then progressively restate every downstream dependency. And not all restatements are needed on account of a bug. Sometimes we simply need to recompute different layers. For instance, a new use case shows up, or an existing definition gets updated to reflect the needs of the business. Another case is compliance-related refactoring, like those that are triggered by regulation. Recently, we finished an exercise to refactor pipelines to keep all personal data from European customers within the European Union. This was a transition that took over a year to complete. A refactoring like that can require recomputing several layers of data as large sections of the lineage graph gets partitioned and moved across geographies. So now we understand the reasons for restatement. But how frequently does this happen? How much effort and resources does it consume? So here are some quick stats around restatements. The number of times we restate data is actually more frequent than the number of times we deploy pipeline changes. This alone should indicate how considerable amount of energy and overhead there is for managing pipelines with this type of complex lineage. A healthy chunk of our capacity goes into sustaining these restatements. 10% doesn't sound like much, but this is over a corpus of 200 petabytes of data. What's also particularly noteworthy is that 1 in 4 times we need cross-data factory communication and coordination between on-call engineers. The scale of the problem makes it very clear that the right tools are necessary to handle restatements quickly and efficiently and without disrupting ongoing operations. In our early years, restatements were still handled manually, and this was quickly becoming a major hit on productivity and cognitive load for on-call engineers. It also became very apparent that we were always going to deal with complex lineage, and restatements would just be one of our concerns. In fact, we had to get really good at managing a number of different aspects about that lineage graph. How we author, test, deploy, monitor, share, govern. All of these would become challenges in their own way without the right investments. So to address this, since 2019, we began investing in a system that we call Nitro. What is Nitro? Nitro is a data ops environment for developers to author and manage data pipelines, to rapidly react to Microsoft's internal data sourcing needs, while handling the operational complexity and the compliance requirements that go with such an operation. It is a system that is built entirely on top of Azure services, including Azure Data Factory, Azure Purview, and integrating with different data processing engines, both public and proprietary. In today's talk, we'll talk only about those aspects of Nitro that are relevant to the data restatement problem. Before we dive in, one key call out. Nitro is a metadata-first system in that its design has an emphasis on developer-annotated metadata, such that all collected metadata is used to either implement runtime behavior of pipelines or for validating runtime behavior of those pipelines. All the visualizations that you've seen to this point are based on such metadata. And you'll see this in critical aspects of how Nitro supports restatement. So let's get into it. An activity in a pipeline is initiated with a trigger that provides an execution time slice with a start and end date. In Nitro, restatement applies only to idempotent activities, which means rerunning the activity with the same execution time slice should yield the same behavior. As I mentioned previously, a significant number of activities consume datasets partitioned by date. And the selection of partitions, although based on the trigger time slice, can encode rich behaviors. They can be conditional to account for specific days or time. The selection can be a single partition or multiple partitions or a partition range if the activity is an aggregator of some sort. They may include offsets, and the offset may be a constant offset or relative to another date. This richness is necessary to allow the system to be flexible to accommodate the range of orchestration patterns. At the same time, this relationship between trigger time slice and the partition has to be well understood and readily accessible. Why is that? Consider a situation where you are alerted to having a bad partition in some dataset. The first step, even before we restate, is knowing which partitions in the lineage graph are impacted. This is essential because this information has to be communicated to consumers that their data in select partitions are likely to be bad on account of some bad partition upstream. Consumers will have to set expectations with their stakeholders. For this reason, Nitro ensures that the selection of partitions for both input and output are based on functions that can be statically evaluated. In other words, knowing the execution time slice allows us to compute the partitions on the input and output of every restatable activity. Additionally, they're also inversible in that given any partition of any dataset, it is possible to identify the execution time slice of the trigger used by the activity to generate it. This feature unlocks another key Nitro capability. Let's go back to the same example shown earlier. Assume we know exactly the problematic partitions on the target dataset. Note that this visual shows only the lineage dependency. It does not show how many pipelines are involved, whether or not they are in the same data factory, how many different triggers are used. Do the triggers have the same window sizes or different ones, like daily, weekly, monthly? But with the ability we just discussed, we can now find the first set of activities which consume these problematic partitions and what output partitions were generated. And we can do it again and again until we have walked the full graph of partitions across every dataset that needs to be restated. We can do this all quickly without running a single job. We refer to this as calculating the transitive closure of partition dependencies. At the end of this calculation, we have the restatement graph, which captures every single pipeline activity and their trigger time slice that needs to be rerun to reprocess data from those repaired partitions. Now, in order to do this reliably, we have to ensure that there is no behavior that a developer may author that bypasses how Nitro understands the relationship to be between trackers, activities, and datasets. Earlier, I had mentioned how Nitro is a metadata-first system. The way a developer writes code with Nitro is first writing these configurations, which capture the necessary metadata. Nitro has a code scaffolding tool that uses this metadata to inject all the right behaviors into the activities themselves. And there are checks in the build pipeline to ensure that these behaviors cannot be modified without also updating the metadata. The metadata itself is pushed into Nitro's operational store with each deployment. So we always have trusted metadata for cases like this one. So far, we've seen how we've looked at Nitro features that support the generation of restatement graphs down to the partition level. We still need a way to replay this graph, and we need to ensure that it happens in the right order. Nitro injects a special behavior at build time for every restatable activity. This behavior generates a tracker file the first time a pipeline activity is instantiated by its trigger for that particular time slice. As long as the tracker exists, subsequent attempts to execute the activity on the same time slice simply skips the operation. Conversely, if the tracker is deleted, then re-triggering it will result in execution. And as we discussed, the behavior is idempotent. Trackers play one more important role. They act as a signal for readiness for activities running in other pipelines or data factories, which may have a different trigger. If a required tracker is not present, such downstream activities will simply wait. With this simple mechanism, we have all the building blocks to build an automatic restatement experience. We know how to compute the restatement graph. We can tell which trackers need to be deleted. We also know which trigger time slices are required to rerun all those activities. What does that restatement experience look like? Nitro provides a portal to keep this workflow simple for developers. They simply identify the root assets that need to be restated. Nitro computes the full restatement graph. The plan is published, which sends a notification to downstream owners with a window to opt out of the restatement if they should so choose. At the end of the period, Nitro kicks off the restatement. It wipes out the trackers associated with the restatement graph, wires up a set of new restatement triggers, which kick in immediately. Pipelines whose upstream dependencies do not have their trackers will simply wait. On-call developers simply monitor for completion. The portal itself will show status as well as notifications when the restatement is completed. And that's it. Now, restatements can take a long time to execute. Hours, days, even weeks. What happens if the lineage graph changes when deployments happen after the restatement is triggered? They're not an issue. An edge that goes missing will simply not be executed. That's okay, because those derivative assets are no longer relevant. A new incoming edge simply means that an activity in the restatement graph has a new dependency when it is rerun. A new outgoing edge simply means that an activity node outside the restatement graph will block until the relevant parts of the restatement graph is executed, which is fine. So there is no reason for a restatement to be interrupted on account of a deployment. Everything you've seen so far has come a long way from about 5 years ago when we were still doing restatements manually, without the kind of tooling that's shown here. So there certainly has been a lot of progress, but also quite a few learnings and open challenges that we continue to pursue. The first learning is that the basics still matter. Pipeline design and data modeling can go a long way in reducing the risk and cost of restatements. For example, choosing to materialize data versus simply using a view. Choosing how strictly you normalize and how much you can delay joins. Placing monitors in depth or only on the aggregates. At the end of the day, all pipeline design is about trade-offs. And restatement-related concerns are just another key design consideration. Another learning is that developers do struggle with the process aspects of coordination. In particular, there is this sense of anxiety when restatements seep in from an external data factory. Conversations often revolve around what the impact would be. Another concern is resource contention. Large restatements can create bottlenecks that can in turn impact SLAs. This is an area where there's still quite a bit of room for improvement. We still struggle with providing developers with an assessment of how significant the shifts in data can be before a restatement. We also struggle with predicting how long and how much capacity a specific restatement will take. Another gap area is around lineage itself. The lineage graph we discuss in this talk is asset and partition-based, not column-based. In other words, in our current graph, we can tell if data set A is derived from data set B. We can tell which partitions in A are derived from which partitions in B. We cannot tell which columns in B were used to compute each column in A. This means that our restatement graphs can be much bigger than they need to be, and we are therefore restating more than we may need to. Tracking columnar lineage is a challenge because understanding the relationship between the input and output attributes of every activity, that requires either reasoning over procedural code, which is really hard, or eliminating it entirely, which is really painful, as there's a lot of rich functionality that is written in procedural code. So an investment area for us is the use of AI to tackle these problems. We have seen promising results from our initial exploration of using LLMs to infer columnar lineage from code. And we are moving to operationalize this to support governance-related use cases, such as data classification, where columns need to be tagged for special handling before applying it to restatement. Another area which is promising is the use of AI to estimate cost and impact of a restatement, to address concerns of on-call developers. And with that, I'd like to conclude. I hope this talk gave you an interesting perspective on the need for data restatement and how systems like Nitro can help with the problem. Before I wrap up, I want to give a shout out to the Nitro team in Ideas, whose work I had the privilege to represent here today. Their dedication to innovation and relentless pursuit of excellence in all things data engineering over the past several years is what allowed me to tell the story. I also want to give my sincere thanks to Meta for organizing this great opportunity to both learn and share. Meta's commitment to fostering these important conversations helps us all to think bigger and bolder. And thank you to my audience. If you're here, your engagement is a reminder that the quest for robust data management is a collective endeavor and a shared commitment to the future of data-driven decision-making. Thank you.
Thank you, Jack, for walking us through Nitro's architecture and its innovative way to manage and support propagation of data changes while ensuring high integrity. Now we would like to invite all speakers for session 2 for a live Q&A with Shilpa. But stay tuned for our final presentation about reliability, performance, and efficiency at scale. Thank you.
Hello and welcome back, everyone. For those of you who is joining us for the first time today, I'm Shilpa Lawande. I'll be moderating the Q&A. Thank you to all our speakers for giving us a wonderful picture of building planetary scale systems. There were 4 diverse talks on completely different systems solving very different problems. And it was nice to see some common patterns and some very different design choices. So without much ado, let me start our Q&A. And for the members of the audience, if you have more questions, feel free to keep adding them to the chat on the website. So Brian, let me start with you. Can you tell us a little bit about how Conveyor is able to provide as much speed as possible to its customers?
Yeah, sure. The interesting thing about Conveyor versus other deployment systems that I've used is that it's able to do a lot of parallel processing. We call it pipelining. And the way that works is say you have like a sample pipeline where you want to build some binary. You want to test that binary and then eventually deploy it once the signal is green, essentially. The way that you can pipeline that is for some release, you're testing some commit hash. You can be building it while another older release can be testing a different version of the binary. And yet even another older release could be deploying some other version of that binary. So by parallelizing the kind of 3 stages of your deployment pipeline, we can kind of eliminate a lot of end-to-end latency there.
Great, that's fascinating. And so this must require a lot of compute and storage to manage all this. Eddie, do you have any thoughts on how you manage this? And it sounds like a very large capacity management problem as well.
Yeah, it's actually not as bad as we think. Conveyor doesn't actually provide resources towards building or deployment. We actually delegate these to other services within Meta to do. So we only hold on to references to, say, the artifacts that we produce during our deployment pipelines, and then hand them off to Twine, our cluster manager, to worry about pushing, or stuff like our CI to do testing. Conveyor itself only has to just maintain getting an artifact from one location to another. So it's actually not that bad.
Great. Switching gears, Braden, how about a question for you? So how do you handle changes in DB sharding in your system when you have to add a shard, say? How do your invalidation components handle that change?
It's relatively straightforward since the system doesn't have to care that much about what's happening with the sharding underneath the hood. So the thing that we get published to us is just what the list of shards is. And that's basically all we know. We also know how to talk to them and where they are, but not anything about what data lives where. And so when that list changes, then our only response is to make sure that we have an invalidator there that is consuming the replication stream off of that shard. And the caches also learn about it so they know which invalidators to talk to. But that's all. It's just basically propagating around a list of strings and making sure that we have enough tasks running.
And so is your invalidation system something like a pub/sub system in this case between the databases and the caches?
There's a couple of different stages there. And so consuming the mutation stream from the databases does happen to involve a pub/sub system for kind of implementation reasons that was easier operationally. So there is a thing that is consuming the replication stream and then dumping it into a pub/sub that we consume rather than us consuming the replication stream directly. But then between the other components inside of LiveGraph, we don't have any pub/sub. There's no further components. All the arrows in the diagram are just live streams. So the caches show up to the invalidators and say, hey, I'm interested in this hash range. And then stuff flows back on the stream.
Great. Sayak, switching over to your system, very interesting system, by the way. How do you balance between reactive auto scaling and over provisioning for spikes? You mentioned that you have very highly variable workload traffic patterns. How do you deal with those competing concerns?
Yeah, so
Yeah, I think I'll take that. So, as we mentioned during the talk, it's a hard problem and we don't have a magic recipe for that. But usually, what has worked out for us is to look at historical data to kind of understand what are the spikes likely, what are the kind of spikes that we might be expecting, and over provisioning our resources a bit for that. Apart from that, also another aspect that is kind of that we try to leverage over here is also the SLA. So what I mean by that is the SLA that we guarantee to the customer. Say something needs to be executed in the next 10 seconds versus something that has the liberty of executing, and for which we have the liberty of executing in the next 10 minutes. For the latter, we can always lean on towards reactive auto scaling more. But for the former, where we have tighter SLAs, we would need to have some kind of over provisioning, as I mentioned. So these two have been the most useful in trying to maintain this balance. But aside from that, we are still we can still improve upon this.
Okay, great. Jack, over to you. Your org, by the way, I love the name ideas for the org, and I also loved the pictures that you had that showed all the lineage, visuals. So, given that your restatements might span multiple teams and across orgs and so on, how do you handle that problem when it crosses organizational boundaries?
Yeah, so that is actually, more heavy-handed than we would like, but in order to facilitate that kind of decision making is precisely why that portal was built. It's basically a place where the restatement owner can get Nitro to effectively notify all the stakeholders, help and push notifications, get the approval needed, and then do the sign off. But it still requires the on-call engineers working for those different sections of the graph to be coordinated in a reasonable time frame. And that's the process that we try to keep, to get the process to scale. That has been, an open challenge.
Very good. So just going back to you, Brian, you talked about your bad package detector as one of your use cases. How do you deal with, how do you know that the diff that was identified as bad actually impacts? What's its impact radius or the blast radius?
Yeah, it's a good question.
Yeah.
Sure. Sorry. It's a good question, and it's a tough problem to solve. I mentioned it in the talk that we do use our build dependency graph to do some level of kind of intelligent analysis to make sure that you're at least referencing the thing that was changed by some commit. But we don't actually know that you're using the specific code in that library that is causing the issue, right? If you have some library that has a bunch of functionality, maybe you're only using 20% of it in your actual application. So currently we don't have a great way to identify that if somebody reports an issue in a library, that you are actually impacted actively by that library. We can assert that you are using the library and using a version of the library that has the problem, but we do have a kind of a noisiness issue with the bad package detector where people will report outages and it will impact a lot of stuff potentially. And a lot of people will say, I don't use that section of the code, but unfortunately, we just don't have a great way today to identify the way to do that. Going forward, we do have plans to allow scoping of these kinds of reported ranges where the person reporting an outage can say, this is only going to be applied to this set of services because I know it's scoped to these services, for example. So that is one idea looking to the future to kind of clamp down on the noisiness issue.
Okay, that makes sense. Let's see. Omar, maybe I'll over to you. How do you detect degradation of downstream services, like other downstream, other than the compute that you talked about?
Right. So this is actually like a quite hard problem. So first of all, it's like as we mentioned in the talk, it's extremely critical for like the async tier to be able to react to degradations to any service in the ecosystem, because for lots of services, um, a big bunch of the traffic going to them comes from the async tier. And as we mentioned, lots of the traffic on the async tier can tolerate some delay. So if we're thinking about whether to prioritize online user traffic versus traffic coming from the async tier, the user traffic always comes first. So this brings into perspective the criticality of the async tier being reactive to the problem. And one of the challenges we had in this space is one simple approach could be, depending on like the user side or like the user function, to signal that some of its downstream has been having a problem and tell us what this downstream is, and then we react based on that signal. However, we've saw that it's not always like a good idea or a reliable approach to count on the users of the async tier themselves telling us what's happening or what was the degradation that was failing in that case. So what we've did is we've worked with the major services in Meta. Most notably of them was Tau, the social graph data store. And what we've built there is a mechanism for those services to directly communicate with async tier on any degradation. And basically here we can just bypass the user side, and there's like reliable communication between async tier and other services such that we can quickly react on those.
Yeah, I'm seeing sort of a pattern of, hard problem of detecting false positives or things of that sort in these systems. Jack, do you see that in your systems? Like, do you have sometimes have to modify your, restatements?
Yes. So we do have cases, and I didn't quite get into some of those details in the talk, but much of the data is under scope of GDPR, and which means that over time, even if there are no code changes, and the data at rest can change in order to keep up with those commitments. And so what tends to happen is when we restate, if it's a deep restatement, there could be changes that may have nothing to do with the original issue, but they may be more attributable to the changes on account of GDPR. So in many cases, that's not really a concern, but there are cases where very hard conversations have to happen if a number moves by 0.5%, because the numbers are that important. And so there's a level of judgment that the on-call engineer has to exercise, and they do have the ability to actually tweak or excuse their sections from a particular restatement. We try and do our best in order to kind of give a summary of the kind of changes or the issue at hand, and then there are cases where judgment has to be applied.
Yeah, that makes sense. Switching gears a little bit, let's talk about availability. I guess all these are planetary scale systems. I would love to hear each of your perspectives on, what availability means to you. How do you maintain availability? Braden, do you want to start?
Sure. I mean, it's obviously extremely important for LiveGraph because we're directly serving stuff to users. They need to be able to see the stuff that they're asking for. We have a little bit more flexibility with sort of the real-time nature of the system, that as updates are getting in, like if there are availability problems that we see there, that manifests as higher latency, and some amount of that is acceptable to a certain point. So we have a little bit of flexibility there, but a lot of the use of the system is just like somebody is trying to load a page and we're trying to get them results very quickly. And a lot of our techniques are the sort of standard ones, which is replicate, add more redundancy of different components. So
this wasn't covered in the talk at all, but all of those components, we actually have multiple of them. We have multiple cache nodes serving the same hash range so that we can flip between them, and there's complicated pre-warming that we do between them, and we have multiple invalidators consuming and all that sort of good stuff.
Sayak or Omar, do you have any thoughts in this area? Omar, do you want to go?
Yeah, I can go. So we actually like have a good if you look at it as from the perspective of people maintaining services, like we have a good property in the system, as in it's an asynchronous platform. So if we can like make a trade-off on something, it would probably be that at a given point in time we would be okay accumulating a bunch of data under any failures, as opposed to like failing or like losing data and all these kind of irrecoverable states. However, for some latency sensitive customers on our platform, again, like the same patterns like Braden mentioned emerge. So for some of those customers, like the near real-time customers, as we mentioned in the talk, we have that concept of multiple shards serving the same customer, and we actually make sure these shards are not like co-located on the same host, such that if like a host goes down, we're still able to make forward progress with other shards. And this is where like the shard coordination comes into place. We mentioned we use Shard Manager, which is also like a service created by Meta, and has like a good paper, which we referred to in the talk. So folks should feel free to check it out. Sayak, anything you'd like to add?
No, I think that covers it pretty much.
Great. Eddie, what happens if conveyor goes down? How do people build packages in that case?
Yeah, so going back to how Conveyor is an orchestration engine, basically, we contact other services or perform other actions on behalf of users to deploy our packages. But I mean, in the case that Conveyor goes down, there's always backups, as in the systems that we directly integrate with. Users can still also directly call these services. So, like for instance, if in the worst case scenario, we don't even have continuous integration anymore, and we have to build locally, users in very emergency situations can try to build packages and then deploy them using Twine or Cluster Manager if it's up directly, or by going to machines directly. Of course, that solution isn't scalable. Conveyor is solving the scalable solution, the scalability problem of having to do that every time. But emergencies can happen.
Great. Thank you. Braden, what do you think is the next scaling bottleneck for LiveGraph?
There are a few that I could see kind of coming down the pipe, and one of them is that because it's a GraphQL-ish system, the fact that the user is asking for something, or the client is asking for something on behalf of the user, that might span across a lot of different databases, right? Because we're going to traverse a lot of edges and look for a lot of stuff. We may run into some kind of elevated availability problems coming up because you're just contacting more machines, and so there's more opportunity for any of them to go wrong. And that one's got some similar solutions that we need to be able to use the redundancy that we have already in the system, which we currently can't, but we have some plans to do relatively soon. We replicate the data among the databases. Right now, we have to read from only the leader copy because there's some complicated linearization of how we see the invalidation stream versus what we find to be visible from the databases. But we've got some interesting stuff we might be able to do about that. And then there are sort of product level features that we want to add that can mark particular pieces of data as sort of non-critical. We're willing to render the rest of the UI, even if this particular thing is unavailable. We have some support for that now, but we want to strengthen that in the future.
Jack, going back to you, I think in your talk you mentioned that sometimes it takes a while for bad data to be discovered and so on. Have you thought about using like ML or any thoughts on how you might speed that process up?
I didn't get into it, but there is an entire data quality subsystem that Nitro has that makes it very easy for pipeline owners to actually add monitors that run in line with the pipeline through the different stages. And in many cases, the places and these also include anomaly detection monitors to look at the time series and see if there's been some anomalies. But the challenges are that in some cases you're detecting shifts in the data, and shifts in the data take time. If you're looking at a monthly metric or a quarterly metric, you're not going to see that if you look at the daily data. That's in some cases by design. And so there is a certain class of issues where I'm not sure ML will help. But there are certainly places where smarter monitors could detect, more subtle shifts in the data. And that's an active area of exploration. The second place where I feel like ML is really promising is in actually helping us limit the scope of the restatement. So if you can make the restatement graph smaller, you can recover faster. And that's something that we've tried historically with ML, but like with generative AI, I think there's so much more potential.
Great. It was interesting that this morning's talks had a system which was using ML for investigations, and so a very analogous problem to some extent.
Yeah, in the AI ops talk, I actually caught it, and I actually sent links to my team. It was a good talk.
Cool. Let's see. Maybe you have time for one more question. Saya, can I ask you? Maybe talk a bit about your flow control. How do you handle that across regions? Sort of at the scale that Meta operates at.
So for handling the flow control across region, as we mentioned during the talk, we have a adaptive logic. So we kind of rely on that to figure out what is the right balance of flow that's required for the specific region. But having said that, in case if some new region comes up or we have significantly scaled up a region, then we would try to incorporate a slow start kind of mechanism where we gradually increase the flow instead of drastically introducing a lot of flow onto the downstream, because that might lead to failures. Yeah.
Great, thank you. Just to close, I was wondering if each of you might share like the biggest lesson you might have learned from building your system. Omar, do you want to start? Like just one takeaway from
Yeah, sure. So I think for me the biggest takeaway is always starting from SLAs, or at least aspirational kind of SLAs, what do we really need versus what do we want, or because we engineers try to always do the best possible, the most performant, the cheapest, all these kind of things. However, I think we sometimes have some leeway to take some informed trade-offs when we speak to customers. And this really helps in setting the right environment of, easier operations, less complexity, all these kind of good things which come from less intertwined systems. So I think that was the biggest learning for me in this scaling journey.
Braden?
Sure. I can't speak for the teams as much, but for me, myself, my background before working on LiveGraph was in databases and file systems and things where there's lots of very hard state. Things are extremely durable and we keep absolutely everything. And LiveGraph is a system with quite a bit of sort of interesting, hairy correctness guarantees that have to be upheld, but all the state is very soft. And that brought quite a number of unexpected challenges.
How about you, Jack? Any?
So for us, I think at least for me, the biggest learning was around how under understood, if I want to use that term, like how poorly understood um, the complexity of some of these lineage graphs that exist in companies are. Like at least when we were beginning rendering this graph, or even trying to explain what this graph looks like, convincing people that there really are so many points of contact as data flows through layers through different parts of the org. That was not a very well understood thing. And then building up an engineering system that can manage the life cycle of something like that. All in all, I think that was a path that we had to walk, and take a whole bunch of our stakeholders along the way. That this thing exists, it's a problem, and it has to be dealt with.
Great. Well, looks like we're out of time. Thank you again, everyone, for a very engaging conversation. And I will hand over back to. I believe we have a small break, and then we will resume again the session number 3. Thanks again to all of you, and it was a great conversation. Bye.
Thank you, Shilpa, and the second session speakers for yet another engaging Q&A. Welcome to the third and the final session of today's event, focused on reliability, performance, and efficiency at scale. We'll start with a talk from Uber. Uber has been on a multi-year journey to reimagine its infrastructure stack. Let's learn about the motivations, requirements, and key features that shape this journey for a hybrid multi-cloud infrastructure world. Please join me in welcoming Curtis Nussbaum, who will be presenting the project codename Crane, Uber's next generation infrastructure stack. Take it away.
Hello, everyone. Welcome to today's talk on Crane, Uber's next-gen infrastructure stack. We're going to go into a lot of interesting details, but if there's one thing you take away from this presentation, I hope it's this. Automation is king. Whatever workflows you have, whatever operations you're doing, automating them is going to give you outsized returns. This is the biggest lesson I've learned in all my years working on infrastructure. I'm Curtis Nussbaum. I'm a senior staff software engineer at Uber. And before we get into all that, let's go back in time to 2018. Uber was scaling like crazy. We were buying servers left and right to try and keep up with the traffic demand. And frankly, our infrastructure was buckling under the load. We found that we were running into three broad categories of issues. The first set of issues had to do with what we call zone turnup, or zone creation. Like many operators of big server fleets, Uber partitions their servers into zones, or availability zones, or whatever you want to call them. We do this to reduce the risk of a correlated failure. We don't want a single power event taking out like half our server fleet. We want to be able to localize those faults. But as we were creating more and more zones to accommodate the increasing size of our fleet, we kept running into the same set of problems. For one thing, our infrastructure stack actually had a lot of circular dependencies in it. What I mean by this is that component A might have a dependency on component B, but then component B wouldn't be able to run unless component A was also up and running. To give you a concrete example, we had a set of software that we used to provision new servers. But that software ran on our compute stack. And we couldn't get our compute stack up and running until we had some servers provisioned. We ran into stuff like this all the time when turning up new zones, and we had to do lots of hacks to work around it. Also, just the process of turning up new zones usually costs us hundreds of engineers across the entire infrastructure org and months of time. As we were scaling and scaling more, this wasn't going to cut it for us. We needed to be able to turn up zones faster. The second category of issues we were running into had to deal with just our day-to-day operations. First, just provisioning servers in and of itself was a manual process. For most teams, what it meant was going to a web UI and going through a series of drop-down menus to configure whatever servers it was they were trying to get into production. As we were thinking about scaling to thousands or hundreds of thousands of servers, this was not going to cut it either. We did have an API backing this web UI, and there was some automation behind it, but a lot of teams didn't know that the API even existed, and the automation was rickety at best. Remediating the servers when problems inevitably arose in production was also a manual endeavor. In fact, it was even worse than that. Teams were left to their own devices when it came to determining if their hardware was even healthy in the first place. And most teams had their own bespoke, custom flows for dealing with problems when they arose. We also just had a really hard time keeping track of all of our servers. We had what we called a host catalog that was a dubious quality. The access controls on it were pretty loose, and we often really couldn't trust what we found in there. Lastly, all of this was specific to our on-prem data centers. This really left us with our hands tied when it came to taking advantage of anything that the cloud might be able to offer us. So with all of this in mind, we set out to design our ideal infrastructure stack. And the guiding principle through all of this was we wanted to reduce operational overhead through automation. So from the very beginning, from day one, zone turnup itself should be automated. Once we had zones turned up, we should be able to scale the size of our fleet to something order of hundreds of thousands of servers. Now, when you get to a server fleet this large, you need a few things. First, your servers need to all be fairly homogeneous. They need to be running relatively the same amount of software. If you start letting bespoke or custom configurations creep in, things get out of hand pretty quickly. We also wanted to be able to treat our servers as cattle, not pets. And what I mean by that is that we shouldn't have any special servers that need to be treated differently than most of the other servers in our fleet. If I can do a set of operations on one host, I should be able to do that same set of operations on every single host in my fleet. Remediation of problems when they arise should be completely automatic. Teams should not be left on their own in terms of determining when problems arise or how to fix them. We should have a single central standard solution for dealing with hardware issues. And lastly, we want all of this to work equally well in our on-prem data centers and in the cloud. And in addition to that, we should work equally well regardless of the cloud provider that we're running on. So let's dive into the details of some of these. Like I mentioned, we wanted automation from the very beginning, including zone turnup. What this meant for us is that the zone should actually be able to build itself, much in the same way that a tower crane builds itself, hence the namesake. In order to orchestrate this zone bootstrapping, we ended up building our own infrastructure as a code framework. This framework allowed us to codify, and when I say codify, I mean literally, in Go code, follow a set of principles that we call layer cake. Layer cake, in essence, says that if I make a graph of all of my various software components, and then draw edges between those components that represent dependencies, I should end up with a DAG, a directed acyclic graph. i.e., there shouldn't be any cycles in my dependency graph. And Podfix is essentially a codified expression of this layer cake framework. If you want to read a little bit more about layer cake, I highly recommend checking out the companion blog post that we have for this presentation. I'll share a link for it at the end. All of this taken together allowed us to turn up a new zone with a single engineer and a laptop in just a few days. So we went from hundreds of engineers across the entire infrastructure org and months of time to single engineer, laptop, in a few days. Pretty impressive if I do say so myself. Furthermore, this whole framework had plugins for both our on-prem data centers and our cloud zones. And the cloud code had plugins for each of the different cloud providers that we wanted to run on. So we would make one abstraction for a particular operation that we wanted to do, say, for instance, setting up a network load balancer. And then we would have different implementations for each cloud provider that we run on. This allowed us to keep our overall code the same over time, while simply adding in new implementations for every new cloud provider that we wanted to onboard to. All right, so we've got some zones turned up now. How do we actually make use of all the servers sitting in those zones? What we wanted was a way to move servers into operation with zero friction. The way we set about doing this was actually creating a goal state system that we call credits. We had a pool of available servers that were sitting, ready, waiting to be assigned in production, and then to actually move them to where they needed to go, we would create a new goal state entry. This entry consisted of a 3-tuple that included the group we wanted the host to move into, the number of servers that we wanted to be assigned to the group, and then the type of server that should be assigned. So, for example, we might say the compute 01 host group should get 300 servers of type N2D. We then had a process called assigner that just constantly monitors our goal state. And whenever it notices a change or an unsatisfied goal state, it'll take servers from our available pool and move them to where they need to go. And as it does this, it will do its best to respect internal fault domains as much as possible. What this means, for example, in our on-prem data centers is that we'll try to be cognizant of the racks in which the hosts that we're assigning are located. So in my previous example, I'm not going to try and bin pack all those 300 hosts into, say, the exact same 3 racks. I'm going to try to get them distributed throughout as many different racks as possible. That way, if there is a rack level failure, it will have minimal impact on the individual host groups. To solve the problem of host provisioning, we actually just obviated the problem completely. All of our hosts come pre-provisioned with the exact same operating system and the exact same set of packages installed. We call this configuration our golden image. And it's actually enforced by a really cool piece of open source software called Dominator. What Dominator does is it looks at the file system specified in the golden image and then scans all the servers in our fleet and makes sure that each of their file system also matches. If it notices any deviations, it simply reverts the change on the host. So if someone comes in and installs a software package that isn't part of our golden image, Dominator will just automatically revert that within a few minutes. This same mechanism also allows us to centrally push out updates. I just simply change the golden image that Dominator is enforcing. All of my servers will now become out of date, and Dominator will gradually, over time, bring them in sync with the new golden image. As we're assigning and moving these hosts around, we're also tracking all of these state changes in a high-quality host catalog. This thing was completely new. We built it from the ground up just for Crane. And it has really tight access controls, which in no small part contributes to a much higher quality of data that we can find within this version of our host catalog. Most of the time, humans aren't even allowed to operate on the catalog itself. It's pretty much just computers and automated systems. We put a bunch of safeguards in place to make sure that people can't futz around with the data that's in here. This gives us high confidence in the data that's located in the catalog, and I can't tell you how useful that is when it comes to debugging problems. Being able to know what a given server is doing at any given point in time with high confidence is incredibly useful. All right, so we've got a bunch of servers. They're in production. Problems are going to inevitably happen. But before we can deal with those, we actually have to define what are problems in the first place. What does it mean for a server's hardware to be unhealthy? This, it turns out, is actually a fairly nuanced question. First, you need to pick what kind of signals you want to monitor. And then, for each of those signals, what kind of threshold and time periods should you look at to determine whether or not the various hardware components are healthy? Let's take, for example, a stick of RAM, just a DIMM. How do I know whether or not that DIMM is healthy? One thing you might want to monitor is ECC error count. Okay, well, what threshold do you want to monitor at? Is 10 ECC errors bad? Is 100 ECC errors bad? And what time window are you going to look over? 10 ECC errors over the course of a year is one thing, but 10 ECC errors over the course of the last minute, well, that's very different. But once we had all the signals that we wanted to monitor and all the various thresholds that we wanted to look at for them, we were kind of off to the races. Then it was just a matter of scanning our servers periodically and checking the hardware signals. So we built a component called Bad Host Detector, and it scans the fleet approximately every 5 minutes. and it just looks at every single hardware signal that we care about for each host. If any of those hardware signals are in breach of our predefined threshold, we then file an issue for that server in a central host issues database. Quick side note, having a database with a track record of all the hardware problems you've ever encountered in production is incredibly useful. You can go back and you can look for patterns and you can find really interesting patterns of failure over time. We then have a third component called Host Activity Manager that monitors this host issues database. Whenever it notices a new open issue, it then, via an API, works with the owner of that host to, as gracefully as possible, drain workloads off of that host. Once all the workloads are drained, it then removes the host into a remediation workflow. That remediation workflow looks a little different in the cloud versus on-prem. In the cloud, it's simply just terminate the VM. It's that simple. We'll let the cloud provider deal with whatever underlying issues are actually going on there. On-prem, it's a lot more complicated. It involves communicating the problems that we've detected to actual humans on the ground in our data centers, and then having those actual humans go out and conduct repairs. That's a whole other complicated process that we could just do an entire talk on its own on. So just doing a quick recap, what we've seen is that Uber has built automation throughout their entire infrastructure stack. From the very beginning, we automate our zone turnup, all the way to our day-to-day operations, which are now more or less fully automated, all the way to detecting any problems as they arise throughout the lifespan of our zones. So where does this bring us today? Well, today, our server fleet spans across several different on-prem zones, as well as zones located in 2 different cloud providers. And with all of this, we've been able to scale our server fleet to just shy of 250,000 servers. Not too shabby, if you ask me. Looking forward to the future, I see 2 main challenges for us. The first is taking advantage of the elastic capacity that the cloud offers us. Crane is actually well poised to take advantage of this with that goal state system I talked about previously. If we want to scale up or scale down, it's simply a matter of changing that goal state. But what we really need are high quality signals that tell us when to do that scale up and scale down. This will involve us working with our partners above us in the stack, the workload schedulers, i.e. the Kubernetes folks, so that they can give us high quality signals when we should change their respective goal states. If it's a Friday night and we're seeing tons of users come online and requesting rides, we need the workload schedulers to tell us that. We need the workload schedulers to tell us that the workloads are currently under stress and they need more resources. And then if it's Sunday morning and things are kind of dying down after a busy weekend, we need the workload schedulers to tell us that, hey, things have let up, you can go ahead and scale us down. We also want to be able to become a little more flexible in terms of the location in which we ingest new servers. Right now, Uber is primarily based in 2 regions, DCA in Ashburn, Virginia, and PHX in Phoenix, Arizona. But utilizing servers outside of those 2 geographical regions is currently quite challenging for us. Now, there's 2 reasons why we might want to do this, or at least 2 main reasons I can think of. The first is cost. DCA in particular, Ashburn, Virginia, is pretty expensive to operate in. So we'd like to be able to take advantage of servers that cost less in regions like, say, the central United States. The second reason is server types. So for instance, GPUs are in very, very high demand right now, and they might not always be available in the geographical regions in which we're currently deployed. So if there's 100 available GPUs in Singapore, we want to be able to take advantage of that. That's all I have for you today. Thank you so much for coming to this presentation. I hope it was insightful and you learned a lot. And of course, if you have any questions, I'm more than happy to answer them. Thank you so much.
Thank you, Curtis, for taking us through Uber's journey of reimagining its infrastructure stack and emphasis on automating everything. As we all know, investing in automating disaster recovery scenarios is fundamentally critical for any planetary scale system. Please welcome Rong Shi as he deep dives in the world of disaster recovery readiness for data warehouse systems at Meta. Take it away.
Good afternoon, everyone. I'm Rong Shi, a research scientist from the data infra Tetris team at Meta. Site-wide outage would cause huge costs in terms of lost revenue and damage to reputation. For example, the 6-hour massive outage in October 2021 cost at least $16 million as revenue loss. For Meta scale that span across dozens of geo-distributed data centers, seemingly rare natural disasters like hurricane blowing down the power lines occur regularly. Furthermore, man-made incidences such as network fiber cuts, software bugs, or misconfigurations can also affect the entire data centers. Today, I'm going to talk about how data warehouse handles disasters, with a focus on how we recover batch workloads at scale. Today's talk includes 3 sections. First, I'll share how DR program was born at Meta and its challenges. Then, I'll give an overview of the data warehouse and our DR strategies. After that, I'll deep dive recent improvements on batch workload recovery. In October 2012, Hurricane Sandy came within 30 miles of 2 Meta data centers, Ash and FRC. The destruction of either data center would have been devastating to Meta business because Ash was a fiber optic cables hub that connect Meta to the rest of the world. FRC contains all of Meta database primaries. At that time, Meta was distributed across only 3 major data centers, and we were not prepared for the loss of an entire region. With plan to grow Meta infra at that time, the likelihood of regional disaster happening was growing. Hurricane Sandy was a wake-up call. We started to ask ourselves if we can run Meta products without one of our data centers. And the disaster program was born as a result. After Hurricane Sandy, Meta started to look at a single region failure model to understand how we can prepare our infra to handle such incidents. This map showed the current deployments of Meta regions across the world. A typical Meta region could contain multiple data centers. Any Meta region could go down due to various factors such as natural disasters or man-made incidents. The strategy for tolerating single region failure is to drain the region. We would redirect traffic away from the affected region towards other healthy regions. There are a few challenges. First, dependencies. Meta runs thousands of microservices, and dependency between all these services lead to a complex operation. And we need to drain systems gracefully based on their dependencies. Second, capacity. It would be problematic if other regions already consume all the available resources when DR happens, and moving more demands to other regions may cause overload. As a result, Meta decided to add extra capacity, called DR buffer, which makes healthy regions have enough resources to absorb the traffic from the affected region without any overload risks. In addition, global replication is introduced to ensure service and data is available to serve workloads even when one of our data centers is down. Finally, failover. For stateless services, we leverage internal tuple service to handle it gracefully. For stateful services, upon failures, states like data need to be recovered and reconstructed in a timely bounded manner. Let's turn to warehouse disaster recovery. Before discussing the DR strategy, let me briefly introduce warehouse at Meta. Warehouse consists of several components that work together to provide a scalable and reliable platform for data storage and processing. Some key components. Data ingestion is the process of collecting data from various sources and loading them into a warehouse. Data sources include user activities from Meta application like Facebook website or Instagram app, and service logs from web services or internal services. Data ingestion is done using the Scribe distributed message system and FBD ETL service. Once the data has been ingested, it is stored in the warehouse using warm storage. Then, compute involves transforming and aggregating the data to create a new dataset, which is typically done using tools like Spark, Presto, and Diagraph. Both ingested and processed datasets can serve different types of workloads. Interactive workloads such as analytics, batch workloads such as hourly updated monitoring dashboards, and ML workload such as training jobs. For Meta scale, warehouse workload cannot fit into one region. Instead, workloads are partitioned by namespace, which is the logical container for data storage and compute. It provides a way to organize and manage the data in the warehouse. A namespace usually contains thousands of tables, and each table could be further partitioned into more manageable pieces called partitions. Namespaces are placed on a specific region or across multiple regions based on namespace resource requirements and available hardware in each region, with the goal to minimize costs over the planning horizon. Now let's talk about the warehouse DR strategy. For warehouse DR, there are two prerequisites: capacity and global replication. Since 2018, warehouse began to deploy extra DR buffer in each region. When disaster happens, the additional capacity enabled the health region to absorb traffic from the affected region without any overload risks. Similar to normal capacity, DR buffer includes data storage, compute, and other resources like I/O. For global replication, warehouse leverage replication system to achieve a replication factor of 2 for each partition landed in the primary region in warehouse. Replication service make extra copy in a different region. This is asynchronous procedure, which means when disaster happens, recent landed data may not have backup copies available yet. As of 2023, replication operates on thousands of meta regions, and the warehouse holds tens of exabytes of data. For daily backup data, replication triggers millions of replication jobs to handle hundreds of petabytes of data copies. What could happen for warehouse users when disaster happens? For interactive workloads, users' query might fail to complete. For batch workloads, pipeline landing time could be delayed and violate SLOs due to data loss. For ML workloads, training time could be wasted due to missing data. Our mission is to minimize all these user impacts. When disaster happens, warehouse would fail over workloads from the affected region to other healthy region and recover missing data accordingly. All these operations are orchestrated via warehouse DR workflow. The prerequisites for kicking off the warehouse workflow, DR workflow, is that DR capacity is ready and the warehouse replication is healthy. The first work phase in the workflow is failover, in which we update corresponding configurations to mark the affected region to disaster status and redirect traffic to other healthy regions. This phase usually takes less than 5 minutes in practice. In reality, there could be a responsible window between the time when disaster happens and the time we recognize it. The second phase is recovery, in which we recover unreplicated backup data while replaying the original pipeline with idempotency assumption. Ingested data can be recovered via Scribe and FBETL services, and batch workload generated data can be recovered while replaying the pipelines. As is shown in this graph, the performance of batch workload replay determines how fast we can recover the missing data, and in the next section, we'll focus on recent improvement on this part. In practice, we conduct different types of DR exercises to validate warehouse DR readiness. First, we conduct tabletop exercises and DR drills with frequent cadency to highlight DR readiness risks and work with partner teams on mitigating strategies. In addition, zero-notice DR storms are meta-disaster readiness exercises where we isolate a whole production region to validate end-to-end readiness for the single region failure. Running storms help warehouse understand dependencies outside of warehouse and potential user impacts. Furthermore, we proactively run their orchestration workflow to mitigate emergencies such as capacity crunch or power loss in a certain region. As mentioned in the previous section, replicating data from the primary region to backup regions happens asynchronously. In addition, data copy could be delayed due to various reasons, such as insufficient capacity to handle burst demands, service overloading, throttling, and transient errors. Considering the warehouse data scale, when disaster happens, there could be considerable amount of recent data that don't have backup replicas yet. Now, the first question to answer: how to locate missing data? Missing data is associated with replication latency. To approximate the replication latency, warehouse use replication lag, which represents the oldest creation time of the data that have been landed yet not replicated. We've been using the replication lag SLA for warehouse DR for a long time. This matrix is easy to get and understand, and if it's under a certain hour, we have high level of confidence that when disaster happens, warehouse can fail over and recover the missing data within bounded time. The biggest issue with using replication lag as a single matrix is that it does not reflect true gap between primary and backup region, as replication system does not guarantee first in, first out semantics. It's very hard to achieve strict FIFO in large-scale distributed systems. In reality, a few replication jobs could be stuck due to various reasons, such as throttling and transient errors. In addition, load imbalance that could be caused by factors like inter-region capacity restriction further complicates the replay range. Our goal is to get exact set of missing data that landed, yet not replicated to the backup region. Given that disaster could happen in arbitrary time, it's necessary to provide a real-time view for the missing data. The solution is to build a real-time replication factor checking service that continuously monitors and updates the delta difference between the primary region and the backup region for any given namespace. After locating the missing data, the next question to answer is how to retrieve the corresponding tasks that generate this data. We need to figure out these tasks and replay them to recover the missing data in the healthy regions. The legacy approach locates all tasks with creation time falling within the window, the replication lag, and failover time. However, this approach is neither efficient nor correct. First, this approach causes quite a lot of redundancy, since it would replay data that had already replicated to the backup region, but still fall under replication lag window. In addition, there are dependencies among tasks, and failing to honor this dependency would incur failures. Here's the illustration for task dependencies. In this example, assuming we have three pipelines A, B, and C, tasks could have intra-pipeline dependencies. For example, task B2 and B3 depends on PB1, the output of task B1. In addition, tasks could have inter-pipeline dependencies. For example, task A1 depends on PB3 as input, which is the output of task B3. For replay, assuming PP3 and PA1 are missing data, we need to execute task B3 first and then A1. Otherwise, task A1 would fail and desired output PA1 cannot be recovered. The key challenge here is to construct dependencies to honor execution order. And this is the key to addressing the two biggest challenges in batch workload recovery: correctness needs and efficiency. The key idea is to leverage data writer to record task information when landing data. For example, when Presto finishes the computation against the input data and writes output to the warehouse, it adds the task information when registering the metadata of the output to the warehouse metadata registry. Then, to retrieve the corresponding task for the given missing data, we can extract the task information from the metadata registry. One more challenge here is that different type of data writers might record different types of task information. For example, Spark only records containing information, and we need to resort to container service to retrieve its corresponding task information. To resolve the problem, we built a translation layer to convert various types of raw information to the standard format. For pipeline tasks, the standard format for a given task is pipeline task name and period ID, in which period ID represents the scheduled time to run the task. Most pipelines run periodically, daily or hourly, and task schedule time is needed to identify which task instances to replay. As mentioned in the previous slides, tasks could have dependencies. Building the full lineage graph to cover all dependencies is a straightforward idea, and we resorted to existing lineage tracking tooling that was built for dependency analysis. However, building full lineage graph is very expensive, and tooling couldn't provide freshness and scalability guarantees of the lineage data. What we need is real-time dependency retrieval. And the key idea to solve this challenge is to leverage the wait-for task, which is a sensor task that delays the following task until the specified data is found, and repeatedly check the data readiness. These key insights allow us to reduce the problem from building a full lineage graph to only retrieving immediate upstream wait-for tasks. Now let's go back to the previous example and see how old and new approach choices work. Assuming the output data for task B2, B4, C1, and C2 are missing, and task B2's output is the oldest data that has been landed yet not replicated to the backup region. The legacy approach simply locates all tasks with creation time later than task B2 and replay them, which includes tasks across all pipelines except the B1 in this example. In addition, quite a few tasks would fail since they are not waiting for dependent data, such as task A1 and C1. In contrast, the new approach locates the exact set of tasks, B2, B4, C1, and C2, and retrieves the immediate upstream wait-for tasks. In this example, we get two wait-for tasks, one for inter-pipeline dependency between B2 and C1, and the other for intra-pipeline dependency between C1 and C2. Then, the new approach submits the minimum set of tasks for replay, and execution order are guaranteed while the wait-for tasks. To handle the scale of missing data in Meta Warehouse, we involved the solution in multiple aspects. For freshness, to reduce the risk of unexpected delays in calculating missing data against large datasets, we built validation logic to periodically refresh missing data report cache in replication factors checking service. For completeness, we conduct extensive analysis to narrow down and categorize the unknown mapping between missing data and tasks, and build corresponding handling logics. And we further filter out unnecessary data and tasks to further minimize the false positives. For scalability, we handle missing data and tasks in batches. To enable this, we involved the solution to batch manner and build batching facilities in corresponding dependent services, such as batch task information retrieval and batch task submission. As a result, we can process large amounts of partitions and tasks in batches with partial failure support. The new recovery approach enables us to recover an accurate set of missing data in disasters, no more, no less. We have demonstrated its effectiveness against production workloads in recent DR exercises. Compared to the legacy approach that could only process tens of thousands of missing partitions, the new approach can easily process more than 1 million missing partitions during recovery. In addition, the new approach can eliminate 75% of redundant recovery and cover more than 10% missed recoveries. It does not end there. Now let's look at what lies ahead for warehouse disaster recovery. As our infrastructure grows, the likelihood of multi-region outage increases, and we anticipate to see such failure happening more often. For example, in February 2021, severe weather in Texas and Nebraska caused power disruption affecting both FTW and PNB regions. Adding capacity is a straightforward idea. However, it is not scalable when the number of region failures goes up, and we need to think about other solutions like service degradation. In addition, ML workloads has a growing footprint in warehouse, and we need to build their compliance strategies for training freshness, such as reducing ML training landing delays during disasters. Lastly, I would say, none of this work would have been successful without vital contribution and support of our team members, data infra partner teams, and partners from storage and core systems. Thanks for listening to the talk. Please do get in touch with us after the talk for any questions. Thank you.
A warm thank you to Ron for guiding us through the intricacies of warehouse disaster recovery system. In the world of mobile apps, one of the fundamental problems engineers need to solve is how to author and distribute configuration changes across a vast and a diverse set of apps, both reliably and efficiently. Mobile config is Meta's internal tool for solving this exact problem. Please welcome Michael Layton, who will be presenting mobile configuration at Meta. Take it away.
Hi, my name's Mike Layton, and I'm a software developer here at Meta, focusing primarily on mobile configuration. Today, I'd like to talk to you about mobile config. Mobile config is Meta's internal tool for the authoring and distribution of configuration values to some of the world's largest applications. Each day, we deploy thousands of configuration changes to billions of users. Mobile config is the key to agile software development here at Meta, allowing our developers to quickly and safely release software at scale. So before we deep dive into mobile config, let's step back and look at where we were when we were doing web development. We had a number of configuration products, everything from A/B test to feature flags, even static values, that allowed us to release software on the web. When we moved into mobile development, we wanted to take those with us. We built mobile SDKs that allowed us to communicate with those configuration products. And that was great and pragmatic. However, it did have some drawbacks. So first, it took a large amount of engineering effort to create each one of those SDKs. Our mobile developers had to learn all of these new tools. And whenever they wanted to switch tools, say go from a feature flag to an A/B test, it required them to make mobile code changes, which can take time. And finally, Meta requires a large amount of scale. So in order to scale each of these SDKs, it also took time and effort. And the problem started to compound. We didn't want to just support iOS, we wanted to support Android as well. And not just Android and iOS for one app, but many applications. In fact, we wanted to support different platforms like Oculus. That's where mobile config came in. Mobile config is a cross-platform SDK that supports all of these different apps and platforms in the mobile world. It communicates with our mobile config evaluation engine, and that evaluation engine can work and provide a single level of indirection to all of our configuration products. Now, mobile config didn't just happen overnight. It's been a journey. So back in 2015, mobile config was first released only on iOS, targeting feature flags and A/B testing. In 2017, we quickly added support for Android. Oculus and Instagram soon followed, and in 2023, we now support Threads and most of Meta's larger applications. That's what we're going to talk about today. First, we'll jump into what is mobile config and why is it hard. We'll look at how we use mobile config to drive agile software development. We'll look at some of the optimizations we need to scale mobile config to work for Meta. And finally, we'll look at the future of mobile config. Mobile configuration at Meta. So Meta has a number of different mobile apps, all running on different platforms and operating systems. Each one of those applications might be written with a different tech stack and different language. everything from Java to Objective-C. And these applications support billions of users. So we need large scale. So what is a mobile config? You can think of a mobile config as really just a key value pair. Each config has a name and a set of parameters. Each parameter has a name, type, and a value. And we provide tools that allow developers to read the parameters inside of their applications. And then we provide tools that allow developers to remotely change those values based on whatever development they're working on. Now, the mobile config client SDK is actually pretty basic at a high level. It's basically just a client-side cache. So this cache is updated periodically throughout the day and on application start. We provide an API that allows us to read from the cache. And then once we provide a value from that cache, we lock it in place so that as the user is navigating different menus and different screens, they're not getting different configuration values. Now we use the mobile config evaluation engine to actually generate the configuration values. So evaluation is the process of taking user context, taking configuration information, and then generating values for a particular user. For example, we have myconfig on the screen here. And myconfig has a number of different parameters. Parameter 1 is tied to a gate. When we run our evaluation for parameter 1 of myconfig, we'll pass user context, we'll pass config information to our gating software, and then it'll check to see if this version of the application is version 1, then we'll return a true. Otherwise, return a false. That's kind of how evaluation works. And we can change the backend that each parameter is tied to. So right now it's tied to a gate, but we could easily switch that to an A/B test or even a static value if we wanted to. Now, none of this would be possible without mobile config's highly optimized cache design. Mobile config is based off of flat buffer, a flat buffer structure, which is great because we can store that flat buffer on disk and we can load it into memory and we don't have to worry about parsing it at all. We also know the exact set of configs that a particular application will use when we build that app. So we can build things called parameter identifiers. And a parameter identifier is essentially just an index into that cache. That means when we do a config read, it's incredibly fast because we're only doing a couple of array lookups. All right, so let's talk about how we use mobile config to drive mobile agile software development here at Meta. So each week, more than 300 major code changes goes into just one of our largest applications. Thousands of developers contribute to our mobile repositories every single month. And we don't actually have control over when an application is updated. Users have control. Any one of these changes potentially cause a regression or a crash in the application. So mobile config is really the solution here. So with mobile config, we can control the feature release lifecycle separately from the application release lifecycle. We can ensure that our configuration changes don't cause issues by using things like mobile config canary. And finally, if there is an issue, we can quickly address that issue by using features like mobile config emergency push. So let's talk about how we could use mobile config to gate a software feature. We could just write the code locally, test it, and then ship it to production. But we all know that there are problems with that. We can't possibly test on the number of different hardware platforms that code's going to run on. And if there's an issue, the only way to fix the issue would be to release a new app version. And we know that users are in control of when they update their apps, not us. So the solution is to put the feature behind a mobile config. If the mobile config value is true, we enable the feature. Otherwise, it's disabled. This allows developers to remotely control when that feature gets turned on or off. It also allows us to completely control the rollout from 0 to 100% of public users. Finally, we could even use a mobile config to run an A/B test. We could tie a button color to a configuration value, for example. And then we can run a test to determine which is the best color for that particular button. In other words, mobile config gives teams the ability to completely control the release lifecycle of their software. One team might run multiple A/B tests, move to a gate, and then release using a static value. Another team might make a very benign change and decide that they want to release it right away and only use the configuration as a kill switch. But either way, mobile config puts them in control of when the software is released. Now, each day here at Meta, we make more than 1,000 parameter changes a day. And there's bound to be some issues caused by these configuration changes. So how do we detect those? And the answer is mobile config canary. Now, mobile config canary is a little bit more difficult than a standard canary. One, we run on a diverse set of hardware platforms, everything from a 15-year-old Android device to the latest and greatest iOS. As we mentioned, we use a pull model to update our cache, which means we have longer propagation times for updating configuration values. And also, Meta provides very feature-rich applications, which means that the configuration might be used deep in sub-menu. And if we only do a short canary, the user might never actually interact with that feature. So how do we solve these problems? That's where mobile config canary steps in. Mobile config canary is a multi-stage canary. In the first stage, we run a pre-land canary, we run it for a short period of time, small set of users, and we're looking for the most critical regressions, app crashes, or restarts. And then, if all of that is successful, we run a post-land canary after we make the configuration change. And we do this for a much longer period of time, 4 or more hours. We target a larger set of users so we can address that diverse set of hardware. And we're looking for a much larger set of health metrics, everything from engagement to app crashes. Now, alone in 2023, this has caught 40 very large issues and prevented them from reaching production. Not all issues can be caught with a canary. And that's where mobile config emergency push comes into play. So emergency push allows us to target a specific app or version and propagate configuration changes much quicker. We also give developers the ability to have options when that configuration is actually changed. So in some cases, we might just update the configuration values, but in others, we might choose to restart the app. This allows us to quickly mitigate issues that might arise in production. Let's talk about a little bit more how emergency push works. So first, we need to detect that there's an ongoing issue happening. Now, we might do that with mobile config canary, but we also just might get a user group post. Once we know there's an issue, we provide a tool to our developers, allowing them to send an emergency push packet to our apps. In this packet, we have an EVN, or emergency version number. We have the name of the configuration value, and we have the option of either restarting or just updating the configuration. And when the app actually receives this information, it'll process it and determine if it's already performed this EVN or not. If it hasn't, it will fetch the config and perform the action. Otherwise, it'll skip and continue. That's how emergency push works. So that's how we use mobile config to drive agile software development here at Meta. Let's take a look at some of the optimizations we need to make mobile config work at our scale. So Meta has a very large scale. We have a number of different mobile applications that we support. We have billions of users for some of those applications. Some of those apps have more than 1,000 different config parameters. And as we already mentioned, we make more than 1,000 configuration parameter changes each and every day. We have very large scale at Meta. So in order to support that, we have a number of different optimizations that we need to put in place. So let's take a look at our client server protocol and some of the optimizations used there. First, we have partial fetch, value hash, schema hash, and Boolean optimization. Let's take a look at each one of them. So partial fetch. We already mentioned that mobile config uses client-side cache to provide values to its API. Now, most of the time we have that cache available, but in some cases, such as fresh app install or app upgrades, we don't. And in those cases, we need to provide something to the API. We could provide default values, but that could lead to older experiences because maybe some feature is getting turned off because we're using a default and not the latest value. We could also stop the application from starting, fetch new configs, and then continue. But that would take a long time to start our applications. So the answer is partial fetch. Here we get the best of both worlds. We take advantage of the fact that only a few configs are needed on start. We fetch those first, and then once we have those, we'll perform an async fetch for the rest. That means that for the apps that are the configs that are used early on, we have non-default values for them. And we don't have to block the app a long time to wait for fresh values. Let's talk about the next optimization. It's value hash optimization. Here we're taking advantage of the fact that even though we have a lot of configuration changes each day, it's highly unlikely that a particular config will change from fetch to fetch. So what we do is we have the server evaluate all the parameters for a particular config, all the values, and we generate a hash for those values. We send the hash down to our client-side SDK, gets stored in the cache. Later, when we perform a fetch, we send those hashes back up to the server. Server reruns evaluation and compares the hash values. If the hashes are the same, we know the client already has the most up-to-date value. We don't need to send new values down to the client. So that drastically reduces the amount of data we need to send from server to client. The next optimization is Boolean optimization. It turns out that about 70% of all mobile configs are just Booleans. And because of that, we can really optimize the protocol. We know all the Booleans that are used in a particular application at build time. So we can provide a known ordering in the server and a known ordering in the client for those configuration parameters. And then rather than sending a JSON blob for each of the configuration parameters, we can send just 2 bits. The first bit tells us whether or not we should return a client-side default, and the second bit is either true or false. And that means that we take our big, large JSON blob with 70% of our configs, and we reduce it to a single string that is base64 encoded, drastically reducing the amount of data we need to send from the server to the client. Now, the final optimization is schema hash optimization. When a client requests new configuration values, it must send the config and parameters to the server. Now, if you're sending thousands of them, it can add up quickly. Since we already know at build time the configs and parameters that are used in a particular application, we can simply generate a hash for them. We store that hash at build time in our database. We also code gen that hash into our client API. Then later, when the SDK needs to request new config values, it simply sends the hash. It doesn't need to send the full set of configs and parameters, making the request much smaller. So this drastically reduces the amount of data we need to send from client to server. Now together, those 4 optimizations present a 96% savings in network payload when compared to not having them turned on, according to our latest experiment. Now we have optimizations like this in our client SDK, in our evaluation engine, and throughout the mobile config system. And if you'd like to learn more about those, please read up on our blog. So we've talked about mobile config, how it's used. Let's talk about the future of mobile config. We know that mobile config supports some of the largest applications. And that means that every bit of performance we can squeeze out of the system, every optimization has huge impact for our customers and for Meta. So we will continue to look for those optimizations moving forward. We also know that the mobile landscape changes constantly. Today, we support Oculus and Ray-Ban stories and a number of Meta's large applications. And as Meta continues to add new platforms and new apps, mobile config will continue to support them. In conclusion, mobile config is the key to mobile software agile development here at Meta. We release thousands of configuration changes to some of the world's largest applications every single day. We allow our software developers to release features safely and at scale. So I'd like to thank you all for listening to the talk, and I'd like to thank the mobile config team for all of the hard work they put in each and every day, as well as anyone who's contributed to mobile config throughout the years. Thank you very much.
Thank you, Michael, for the great technical deep dive into this interesting problem space. Now we would like to invite all the speakers for the session 3 live Q&A.
Hello and welcome back, everyone, to this last session of Q&A for our Systems at Scale Winter Edition. I am Shilpa Lawande. I'll be your moderator for this Q&A session. So thank you to all the speakers who gave us these wonderful talks on performance and reliability at scale. We learned about Uber's next-gen infrastructure, Meta's warehouse data recovery, data warehouse recovery, disaster recovery, as well as mobile configuration at Meta, all very interesting and very different systems. So let's get started with our Q&A today. So Curtis, let me start with you. What are some advantages and disadvantages of operating in the cloud versus on-prem?
Yeah, it's really interesting operating on these two very different kinds of platforms. On-prem, some of the advantages that we have is we actually have a lot of introspection into how the data center itself is laid out, and therefore we can know things like internal fault domains. So in all of our on-prem data centers, I know which rack every single host is in, and I can be intelligent about the way I schedule workloads such that I can help them avoid rack level failures. One of the major kind of disadvantages of operating on-prem is actually just acquiring the servers themselves, right? When you're purchasing actual physical hardware, you've got things like long lead times, having to negotiate not wanting to kind of get locked into a single hardware vendor, so needing to manage multiple vendors. And then kind of conversely, on the cloud side of things, capacity management's a little bit easier, by no means super easy. At the scale that we're working at, we actually have to have very close contact with our cloud partners and let them know what our kind of scaling schedule is going to look like. The cloud, as it turns out, is not as elastic as one might think when you start talking about, say, thousands of servers. So we do have to give them some kind of runway there. But then obviously, as long as we kind of give them good forecasts and give them, order of weeks heads up when, big new demands are coming in, they can usually meet those demands without much of an issue. So those are kind of some of the major things. I'd say the other thing with the cloud is maybe we kind of have access to a more diverse set of machine types. But then I would say the other disadvantages of working in the cloud is that to really take advantage of the cloud, you need to be able to operate in multiple geographic areas. And I kind of alluded to this in my talk. A lot of companies solve this problem by just saying they pick one region and they're like, yep, cool, that's the region we operate out of, and they try and scale just within that region. At Uber scale, that's becoming harder and harder for us to do. We need to figure out a way to be able to take advantage of what the cloud gives us in multiple different geographic areas.
Yeah, makes sense. I mean, many of these problems are similar to things we encounter at Meta as well. So switching to you, Michael, can you talk a little bit about your approach to mobile config canary? You mentioned a multi-prong approach of a shorter pre-land canary and then a longer, more in-depth post-land canary. Why do you do that? Why not just run the pre-land canary for a longer time?
Sorry about that. That's a great question. It really has to do with a trade-off between developer efficiency and trying to catch every single issue. So mobile config is so embedded in our developers' workflows that we want to make that process as quick as possible. So if we were to run a very long canary before we could make a configuration change, that might slow down developer efficiency. So by breaking it into a multi-stage approach, really get the best of both worlds. We're able to detect the most critical issues very quickly, and then we're able to land the configuration change, and then watch it using that post-land canary to detect if there's any other issues.
Great, thank you. Abhishek, question for you. How does the warehouse handle regional failures that are sub-region, where the whole region is not down?
Yeah, that's a good question, Shilpa. So essentially, when we plan
our warehouse DI recovery, we look at the entire gamut of failures that can happen. We develop our services in a fault-tolerant way. So a large variety of faults can be handled within the region by the services themselves. But then we have policies on the extent of the fault and the kind of faults that are going to have a higher impact by trying to mitigate them within region. And based on those policies, we take decisions on when it makes sense to fail over and handle those sub-region failures through entire region being failed over. The ROI decision is based on how much time would it take for us to get back to normal operating conditions after failover versus how much time it would take for us to try and recover within the region. In addition to that, we also have strategies to account for additional capacity we need for regular maintenance so that we actually test sub-region faults as well. That complements our overall region level failover strategy. Back to you, Shilpa.
Sticking with region failures, then, Ron, do you want to talk about multi-region failures? Like, what do we have a strategy for that?
Sure. Yeah, good question. As mentioned in the presentation, like as our infra grows, the likelihood of multi-region outage increases, and we anticipate such failures to happen more frequently in the future. Our DR strategy is focused on two dimensions. The first dimension is data availability. Warehouse leverage additional data replicas, to improve the data availability. Try to reduce the probability of the data loss when disaster happens. Given that the capacity is bounded, warehouse would categorize the data and workloads based on the business impacts and allocate capacity accordingly. On the other dimension, the service availability, warehouse would apply site degradation strategies like service level degradation or delaying non-critical requests or workload jobs. This can help to free up some capacity that can be used as the complementary solutions for the DR physical buffer.
Got it. And just sticking with the failure topic a little bit, Curtis, how does bad host detector scan your entire server fleet in 5 minutes? Sounds amazing.
Yeah, so the problem is actually IO bound. The first way we get these kinds of fast scans is, first of all, the thing to remember is that bad host detector is operating zonally. So I have one instance of the service operating for each zone. So immediately, the number of hosts that any instance of bad host detector needs to scan is only going to be like a certain partition of our fleet. But then really after that, it's just IO bound. So there is a single agent that's running on every single server in our fleet. This agent is installed on the golden image that I mentioned. And it just has an endpoint where we can scrape a bunch of hardware metrics. And so really the problem comes down to is how fast can BHD scrape metrics from each of the servers in our fleet? Because analyzing those metrics is actually like very straightforward. Most of what we call checkers are super simple. They're like, look at metric value, does it exceed threshold? And like, that's it. That's all we have to do. So the lead that I kind of buried in that slide about bad host detector is, yes, we have very fast scans. We're able to scan the entire fleet very quickly, but that's just our time to detection. The thing that actually matters to most of the teams at Uber is time to mitigation. Because if I leave a host that, say, has a bad NIC, or maybe just like a flappy NIC, running in production for, say, 30 minutes, that's 30 minutes of whatever workloads are running on that server having elevated error rates. And so a lot of what we're doing, the team that works on that particular component, a lot of what they're doing kind of going forward is looking into how do we actually reduce the time to mitigation, because that's what really matters for us.
Great, thank you. Switching back to you, Michael, can you talk about a few examples of why we have multiple different ways to access the backend configs?
Yeah, absolutely. So there's actually a number of different use cases that this supports. a developer might want to run an A/B test, for example. So they can put in a configuration value, run an A/B test, and then decide whether or not they want to release that feature. And then without making any code changes at all client side, they can switch that back end to something like a gatekeeper or a rollout tool that will allow them to roll out that feature from, say, 0 to 100%. That's one of the use cases you might use that for.
Great. Just on the use case topic, Rong or Abhishek, what is the DR strategy you have for ML workloads, and how is that different from other workloads in the warehouse?
Yeah, that actually is a very exciting area, Shilpa, and I would not go into too much detail, because of there's some things that we're working on in proprietary knowledge, but it is definitely a very major focus area for us right now. And I can talk about sort of the broad challenges that we see, which are new to ML workloads, which are sort of not something we've seen before. One is because of proliferation of prioritization of ML as a focus area, there's a lot of velocity in new hardware types coming up, and ML models are very sensitive to hardware types. When you train, if you change the hardware type, the sort of characteristics of that model change. So as much as possible, ML engineers, they want to train on consistent hardware types. And the way that creates a challenge is there's a lot of demand and a lot of diversity, right? We're sort of coming up with new hardware types every few months these days. How do we formulate a way in which DR can allow the right hardware types to be available for the right workloads, given the scale at which we operate and given the diversity? So that's challenge one. The second challenge that is very interesting for ML workloads is the most critical revenue powering workloads are also very sensitive to freshness, right? You want to close the loop between events happening all the way flowing through the system and the model getting trained on them so that we can respond based on the activities as fast as possible. And this becomes a very interesting challenge for DR, because now when we fail over, how can we design our failover strategy to ensure that the most critical models which require the freshest data actually have the ability to continue to operate when we have a region failover? So freshness and diversity and scale of capacity, these are the sort of two big areas based on which we are putting together our warehouse DR strategy for ML. Thanks.
Great, thank you. Speaking of challenges, Curtis, would you like to tell us, what were the biggest challenges you ran into throughout this project?
I think the biggest challenges weren't necessarily technical. It was getting everybody to row in the same direction. Crane really cut across pretty much every single team that works in our infrastructure org. And so getting everybody aligned and on the same page and getting everybody to agree to what are the APIs going to be, what are the terms going to be, what are the SLAs going to be. That was probably the biggest challenge we had, especially because there were certain teams that were coming from very different kind of philosophical standpoints about how one goes about operating infrastructure. We had certain teams that were just very DevOps heavy, and the idea of doing a lot of automation and taking humans out of the loop actually was kind of scary isn't the right word, but it felt like a loss of control, and therefore we might cause more outages by not having humans in the loop. So getting everybody to kind of believe in the vision was probably the biggest challenge that we faced.
Great. There's actually a question for you from the audience that I will ask. Do you have any guidelines on estimating racking, stacking, infra, capacity management, cost estimation, and so on?
I play a lot of Dungeons and Dragons, and I like to make the joke that you approach a ambiguous conference room on floor 5 of your office building. You hear a bunch of yelling and shouting, and there's a sign over the top of the conference room that says capacity management. Roll for initiative. It's really, really tough to predict this stuff because you have so many different people trying to trade horses and get the capacity that they need, all the while the business is putting the pressure on you of keeping costs in control. You know, you can't just buy every single server that every single team wants. You need to make hard decisions and hard trade-offs. I don't work on the team that actually does the capacity forecasting, that does the server capacity forecasting, but I work closely with them because a lot of what we do involves making sure that the capacity that they get for us then ends up in the right hands. So I'm gonna like I don't want to misquote them or anything, but generally the way the process works is they look at past trends, right? And they make a prediction. There'll be like a graph of like with like a linear regression of, okay, if we keep scaling exactly the way we've been scaling for the last, year or so, we'll do this. And then there's error bars on that of like, if we go 2x higher, we'll need this much. If we go 2x lower, we'll need this much. And they kind of try to thread the needle in that respect.
Cool. Yeah, it is a very challenging problem. We also experience this all the time at the scale of Meta. Michael, another question for you. You mentioned using a pull model to periodically refresh configs. Like, did you consider trade-offs with a push model instead?
Yeah, that's a great question. So the reason we use a pull model is all about really scalability. It's not super important that mobile config has the latest value instantly because we actually lock values per a given session. So even if we were to distribute the latest configuration values to all apps instantly, they won't actually be used until the application's restarted. So by using a pull model, we have a little bit more control, the traffic's a little bit more predictable, and we don't have to use up a ton of resources when we're actually doing our syncing. Gives us a little bit more flexibility there.
Great. Ron, another question for you. How do you measure DR readiness or user impact in the warehouse?
Sure, good question. To measure like DR readiness or user impact, we follow the industry standards, RPO and RTO matrix. RPO represents the recovery points objective, which is the amount of data that can be lost before significant harm to the business occurs. The RTO means the recovery time objective, which is how much time the application can go down without causing significant damage to the business. Now, for warehouse, the RPO is defined as a freshness loss due to the replication latency that is mentioned in the presentation. About RTO, for interactive workloads, it is the delay introduced due to the disaster detection plus the failover process duration. For batch and ML workloads, it also includes the landing delay introduced due to disaster events.
Great. Okay. Well, I think we have a couple of minutes, so maybe I'll ask you all to talk about, what is one big lesson you've learned from building the systems that you talked about today. Let's start with you, Curtis.
I think I'll just go back to kind of what I said in my presentation, which is that, in all the last years that I've been working on infrastructure, I've just really kind of come to very much appreciate the power of automation. It's automating things like all the way, not getting like 90%, and then there's like one thing that like, has to go and a human has to go like click a box somewhere to like say yes and approval. It's like fully getting things completely automated. When you see that kind of a system work, that there's just no humans in the loop and it automatically heals itself whenever there's problems, it's so amazing. Right now, like at anywhere in Uber, with maybe one or two exceptions, I can just go and like rip the power cable from one of our racks, and nothing will happen because, of course, everything we run is like generally run in a highly available fashion. But those servers will be detected automatically that they're now offline. They will be moved into a repair queue, and then immediately, within like 5 minutes, servers that are waiting in the wings that are on standby will be pushed into production, and new workloads will just automatically start running. I think it's some of maybe like the bigger companies, this is kind of old hat, and yeah, of course it works that way. It wasn't that way at Uber just a few years ago. And so to watch us go through that transition of from, hey, we kind of need to handhold certain processes one way, or another, and to make sure that if something goes wrong, they come back in a healthy manner. To just, nope, there's no humans in the loop. Like in the middle of the night, some servers go down, nobody cares. There's nothing happening. It was just a really amazing transformation for me to watch.
And it frees up the engineers to work on more interesting things, right? Yeah.
Absolutely.
Yeah. Michael, how about you? What's your learning?
Yeah, I guess my big learning is just that mobile configuration done right really can drive developer efficiency. If you give developers all of the tools that they need to release software safely, like at a large scale, they're really capable of taking advantage of that and being extremely efficient. So I think that's my big learning.
Great. And last but not the least, Rong and Abhishek, one or both of you want to chime in?
Yeah, I can take this. I think as Rong presented and similar to what Curtis responded, I think the biggest lesson for us was the rigor of continuous testing for region loss is the most important thing. And we can talk about strategy and all those cool things we do, but it's really that continuous testing that we do that has revealed many surprising things where people have made assumptions about the services that we only discover when we actually do the testing. So to have like a good solid DR failover solution, the most important lesson is like regular and continuous testing across all your regions.
Great. So I heard good developer tools, good continuous testing practices, and automation everywhere. Right. So thank you for sharing those lessons. They apply to not just these, but many, many infra systems. So thank you again for joining us with the great presentations, as well as engaging on this Q&A conversation. And with that, I will hand back to Beren for closing comments.
All right, everyone. That brings us to the end. And I hope you have found as much value in this content as we did in bringing it to you. You can find the talks and the corresponding blogs on the @Scale website. And please stay tuned for more information about our next event, Real-Time Communication at Scale, taking place in the new year. Thank you.